Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, questions slow down, and the universe is allowed to explain itself at a gentler pace. Tonight, we're settling into a mystery that may be closer than your walls, nearer than the floor beneath your feet, and perhaps moving through you this very second without the slightest fuss. Our subject is dark matter. It has one of those names that sounds dramatic enough to wear a cape, but in truth, dark matter is not evil, not spooky, and not lurking in corners waiting to jump out at astronomers. It is simply dark because it does not shine, it does not glow, it does not reflect light into telescopes like stars, planets, or your neighbour's unnecessarily bright porch lamp at midnight. And yet, despite refusing to be seen, it appears to be everywhere. That includes the vast reaches between galaxies. That includes the invisible scaffolding holding cosmic structures together. That includes the regions surrounding our own Milky Way. And if current science is correct, that includes the very room where you are listening right now. So before we go any further, let me ask you something soft and simple. Where in the world are you tonight? Are you tucked beneath blankets while rain taps gently on a window, resting in a city apartment with distant traffic humming below? Lying awake in a quiet house where every creak suddenly sounds much more important after dark? And what time is it where you are? Perhaps it is late enough that the day has loosened its grip. Perhaps it is early morning and sleep has not quite arrived. Maybe you're listening during an afternoon pause, stealing a small pocket of calm from a busy schedule. Wherever you are and whenever you are, I'm glad our paths have crossed in this little corner of thoughtful quiet. If you find these slow journeys soothing, interesting, or simply helpful company while the mind unwinds, I'd be ever so grateful if you gave the video a like, maybe subscribed, and joined us again sometime. It helps this calm little signal travel outward to others who may need a gentle landing place. Now then, let's return to the odd idea that you may be surrounded by something invisible and enormous in significance. Most of daily life trains us to trust what we can detect directly. We see the table, so we believe in the table. We hear the kettle whistle, so we know tea is on the way. We feel the wind, so we accept that air is moving, even though air itself is invisible. We smell toast, so we know somebody nearby made an excellent decision. But the universe has never promised to limit itself to our senses. There are many things we know are real because of their effects rather than their appearance. Gravity is a familiar example. You cannot hold gravity in your hand. You cannot pour it into a mug or point to a floating blue cloud labelled "Gravity, here it is." Yet when you drop your keys for the third time this week, gravity participates immediately and with great confidence. Magnetism is similar, radio waves too. So are X-rays, infrared light, ultraviolet light, and the countless signals crossing the room right now carrying data, music, messages, maps, and probably a recipe somebody forgot to finish reading. Reality is full of things that do not bother to announce themselves visually. Dark matter belongs to this family of hidden participants, though it may be the most impressive member of the group. Scientists did not invent dark matter, because they wanted a mysterious phrase for documentaries. They proposed it because the universe behaved as though extra mass existed. Galaxies spun in ways they should not spin if only visible matter were present. Clusters of galaxies held together more strongly than expected. Light bent around unseen concentrations of mass. Large cosmic structures formed in patterns suggesting that something substantial had been there from the beginning, helping guide ordinary matter into place. Again and again, nature seemed to say, "You're missing something," and so researchers listened. Imagine entering a room and seeing curtains sway though every window is closed. You might not see the cause immediately, but you would know some influence is at work. Maybe a hidden vent, maybe a draft under a door, maybe a ghost with excellent timing. You would not shrug and say, "Well, curtains simply do that." In much the same way, astronomers watch stars orbit galaxies too quickly, watched galaxies cluster too strongly, watched gravitational lensing reveal mass where little light existed, and concluded that some unseen component was present. That component is what we call dark matter. Now, if the name makes it sound like a thick black fog pooling under furniture, allow me to reassure you. Dark matter does not seem to behave like smoke or dust or liquid shadows. It does not gather in puddles. It does not stain the carpet. It does not creep dramatically down hallways while violins play. Instead, it appears to be spread through large halos surrounding galaxies, including our own Milky Way. Picture our galaxy not as a flat disk alone, but as a bright spinning island nested inside a much larger invisible cloud of mass. We cannot see the cloud directly, but we can infer its presence through gravity. That means our solar system moves through this galactic halo all the time. The Earth orbits the Sun. The Sun orbits the centre of the Milky Way. The Milky Way moves through space, and throughout this grand layered motion, we are believed to be travelling through a region filled with dark matter particles passing quietly by. No fanfare, no tapping at the window, no dramatic soundtrack, just an invisible cosmic background. It is one of my favourite facts in science that the strangest truths often arrive with the least drama. Somewhere beyond the ceiling above you, stars are exploding, black holes are colliding, galaxies are merging, and a vast amount of unseen matter may be streaming through your neighbourhood with all the emotional intensity of polite rain. You might wonder, if it is here, why don't I notice it? A sensible question. You do not feel dark matter for the same reason you do not feel sunlight pass through a closed eyelid as individual photons, or hear Wi-Fi brushing past your shoulder. Dark matter, as far as we can tell, interacts extremely weakly with ordinary matter. It has gravity, yes, but it does not seem eager to bump into atoms, light up molecules, or knock over lamps, which is excellent news for the lamps. In practical terms, countless dark matter particles could pass through your body every second and leave no trace you can sense. Through skin, through walls, through oceans, through mountains, through the Earth itself. Not because they are magical, but because the chance of interaction appears incredibly small. That may sound unsettling for about 3 seconds, until you realise something similar is already true of neutrinos. Trillions of neutrinos from the Sun pass through you each second, and you have likely handled this news admirably so far. The universe is busier than it feels. Part of the calm that science can offer is this reminder. Reality contains vast hidden traffic, and yet your pillow remains a pillow, your room remains your room, and your evening can remain pleasantly ordinary. Still, there is something wonderfully humbling in the thought that human senses, useful as they are, sample only a sliver of what exists. Our eyes evolved to notice the wavelengths useful for survival, not to reveal the full inventory of the cosmos. Our ears detect a certain range of vibration, not every murmur of nature. Our instincts are tuned for meals, weather, shelter, and whether that rustling bush should be respected from a distance. They were not designed to detect invisible galactic matter. That task required telescopes, mathematics, patience, and many people willing to spend years studying tiny discrepancies that most of us would call close enough. Science often advances because somebody refuses to ignore a mismatch. A star moves too fast, a galaxy bends light too strongly, numbers do not balance. Rather than smoothing the problem away, someone says, "No, wait, something matters here." That stubborn curiosity has revealed astonishing things. It told us Earth circles the Sun. It showed us atoms, germs, radio waves, expanding space, and planets around distant stars. And it may have revealed that the majority of matter in the universe is not the kind that makes trees, oceans, sandwiches, or sleepy listeners. Instead, most matter may be dark. Not dark in mood, not dark in morality, simply dark to light. There is a difference, and an important one. If you're listening in bed right now, perhaps glance around the room in your mind. The dresser, the blanket, the shelf, the glass of water you promised yourself you would remember tomorrow. All of it is made from ordinary matter, the familiar atoms of everyday life. Yet according to current cosmology, this familiar category is the minority share of the universe's matter budget. We are, in a sense, built from the uncommon visible portion, living inside a much larger hidden framework. That can sound eerie if phrased badly, so let's phrase it well. It is not eerie, it is expansive. It means there is more to reality than first impressions suggest. It means the cosmos still contains genuine mystery. It means after centuries of investigation, humanity has not reached the dull ending where everything is known and labelled. Far from it. We still live in an age where one of the main ingredients of the universe remains unidentified, and perhaps there is comfort in that. The world can still surprise us. Step for a moment into an ordinary room and notice how much of your life depends on things that never introduce themselves properly. The air around you is the first example. It surrounds your skin, fills your lungs, carries sound to your ears, moves curtains, cools tea, and occasionally steals important papers from desks when a window is left open at precisely the wrong moment. Yet most of the time, you do not think about air at all. It is invisible, constant, and polite enough to do its work without applause. Gravity is even quieter. You have never seen gravity directly. You have seen what it does. It keeps your feet on the floor. It guides rain downward. It encourages dropped toast to choose the least fortunate landing angle. It holds oceans to Earth, Earth to the Sun and the Moon in its familiar path overhead. But gravity itself does not arrive wearing a name tag. Then there is warmth. You may feel it from a blanket, a radiator, sunlight through glass, or a mug held between your hands on a cold evening. Yet heat is not a glowing substance flowing visibly into your fingers. It is energy moving through matter, invisible until its effects become obvious. Already the world begins to look different. We often imagine that reality is mostly made of visible things, with a few hidden exceptions tucked into corners. But in truth, much of existence is known through consequence rather than appearance. We detect the unseen by noticing what changes when it is present. That is a useful thought to keep beside us tonight, because dark matter belongs to this long tradition of invisible realities. Before we return to galaxies and cosmic mass, let's stay close to home for a little while longer and explore the feeling of something you cannot see. Have you ever entered a room and sensed that someone had just been there? Perhaps a chair is slightly out of place. A warm mug sits on a table. A door still swings gently on its hinges. Maybe there is the faint smell of coffee, soap, perfume or toast. You do not witness the person directly, yet traces of their presence remain. The mind is remarkably good at reconstructing hidden causes from visible effects. A branch moves. There was wind. Footprints appear in snow. Someone passed through. A spoon vanishes from the kitchen drawer. Either a family member borrowed it, or your household has entered a deeply inconvenient mystery. This ability is ancient and practical. Long before mathematics or telescopes, animals survived by noticing indirect signs. A rustle in grass could mean predator, prey, or simply dramatic grass, but paying attention mattered. Humans inherited brains eager to infer causes from patterns. Science refines that instinct. Where instinct says, something changed, science asks, how much, under what conditions, and can we measure it twice? That careful habit is what eventually led us toward dark matter. Yet there is another side to the unseen, one that belongs not to equations but to feeling. Sometimes what cannot be seen feels larger precisely because it leaves room for imagination. A house at night can seem full of possibilities because shadows conceal details. A sound behind a wall becomes interesting because the source is hidden. The future itself can feel overwhelming because it has not yet taken visible form. When we cannot see a thing clearly, the mind often fills the gap. That is why invisible realities can become spooky in stories, magical in folklore, or unsettling in half-awake moments at 2 a.m. when the coat on the chair suddenly appears to be considering movement. Dark matter receives some of this treatment because of its name. If it had been called non-luminous gravitational matter, Fewer novels would have been inspired, but more people might have slept peacefully. Instead, it was called dark matter, which sounds like something discovered in a forbidden basement beneath a castle. In truth, it is likely much less theatrical. It does not appear to whisper. It does not ooze. It does not gather around candles. It does not rearrange furniture when nobody is looking. It simply seems to have mass while interacting weakly with light and ordinary atoms. Quite respectable behaviour, really. Still, our emotional relationship with the unseen matters because it shapes how we think. Many people are comfortable with invisible Wi-Fi but uneasy about invisible cosmic matter. Yet both are examples of something inferred by effects rather than directly sensed. One lets you stream music. The other helps hold galaxies together. Different scales, similar principle. Consider magnetism for a moment. Place a magnet beneath a sheet of paper and sprinkle iron filings above it. Suddenly the filings arrange themselves into elegant arcs and lines. The magnetic field itself remains unseen, but matter responds to it in visible ways. The field is revealed by behaviour. Dark matter is similar in spirit, though vastly grander in scale. Stars move, galaxies rotate, light bends, structures form. Matter responds to something hidden. The hidden influence becomes visible through motion. This way of knowing asks for patience because it lacks the satisfaction of pointing at an object and saying, "There it is." Instead, it says, "Look carefully at what everything else is doing." That can feel less intuitive at first, but it is often more powerful. You do not need to see the wind directly to understand storms. You study trees bending, waves rising, pressure changing, clouds moving. The invisible becomes legible through patterns. Likewise, astronomers study the motions of stars the way sailors once studied currents. If stars orbit too quickly, something adds gravity. If galaxies remain bound when visible matter seems insufficient, something adds mass. If light from distant objects bends more than expected while passing through space, something lies in the path. Again and again the universe gestures toward unseen structure. There is something deeply human in resisting this at first. We like solid categories. Seen means real. Unseen means doubtful. Yet history keeps correcting that instinct. Microbes existed before microscopes. Radio waves crossed space before radios. Atoms shaped chemistry before anyone imaged them. Continents moved before plate tectonics explained how. Reality does not wait for our instruments. It simply continues being real until we catch up. Perhaps that is why scientific discovery can feel so calming. It reminds us that mystery is not chaos. Hidden things may be unknown, but they are often orderly once understood. Lightning once seemed divine, random, or terrifying. Now we know charge separation, electrical discharge, atmospheric conditions. It can still be dramatic, but it is no longer pure confusion. The same may one day be true of dark matter. At present, we know some of what it does and much of what it is not. It does not emit light. It is not made of ordinary atoms in sufficient quantity to explain the missing mass. It does not clump into shining stars the way regular matter does. It interacts weakly, at least with known forces beyond gravity. That still leaves room for many possibilities. And room, interestingly, is where invisible things often become noticeable. Walk into a cold room and you feel temperature. Enter a silent room and you notice sound's absence. Step into a crowded room and sense social tension before anyone speaks. Humans are sensitive not only to presence, but to patterns in space. You know when a room feels restful. You know when it feels tense. You know when furniture has been moved by someone who claimed they barely changed anything. These impressions are built from subtle cues below conscious awareness. In a way, science does something similar with the universe. It notices that cosmic rooms feel wrong under certain assumptions. Too much motion here, too much lensing there, too much structure too early. Something unseen seems to be occupying the space. Of course, unlike you noticing that the sofa has shifted 6 inches left, astronomers require data, models, and years of work. But the spirit is related. Infer hidden causes from altered surroundings. There is another comforting lesson hidden here. You are already adapted to living among invisible realities. Every breath trusts gases you cannot see. Every step trusts gravity you cannot touch. Every sunrise depends on nuclear reactions inside a star you cannot visit. Every phone call relies on electromagnetic processes too small and fast for senses to track. You're not a stranger in an unseen universe. You're an expert resident of one. Dark matter, then, is not an alien intrusion into human understanding. It is an extension of a familiar theme. Nature contains layers beyond direct perception, and we learn them through effects that may even apply to daily life more than we admit. Kindness is often invisible except in results. Stress can be unseen except in posture, sleep, tone of voice. Trust cannot be photographed directly, yet entire relationships depend on it. Habits shape futures quietly. Time itself cannot be held in your hand, yet everything changes within it. Some of the most powerful forces in life are known indirectly. Now, to be clear, dark matter is a physical scientific topic, not a metaphor for emotions or values. But our comfort with indirect evidence can be strengthened by noticing how common it already is. You do not demand to see gravity before using stairs. You do not refuse air until it becomes visible. You do not question music because sound waves arrive unseen. So perhaps it is less strange than it first appears that much of the universe may be known through motion and mass rather than sight. Imagine for a moment that human eyes had evolved to detect dark matter interactions directly. The night sky might look entirely different. Galaxies could be wrapped in glowing halos. Rooms might shimmer with faint streams passing through walls. Space itself could seem crowded where we now perceive emptiness. But we evolved for forests, plains, weather, faces, fruit, footsteps, and the practical business of staying alive. We did not evolve to inspect galactic mass distributions, so we built tools. Telescopes extended sight, spectrometers extended colour, particle detectors extended touch into realms too subtle for skin. Mathematics extended intuition where senses fail. That last one is worth appreciating. Equations are often portrayed as dry symbols, but they are one of humanity's most elegant sensory organs. They allow us to detect patterns where eyes cannot help. When numbers disagree with expectation, they are telling us something. Dark matter first entered science not through a dramatic visual reveal, but through numbers that would not behave. Mass estimates were too small, speeds were too high, gravity seemed undercounted. The cosmos politely but firmly refused the visible-only version of events. Soon we'll explore those specific clues in detail, especially the strange behaviour of galaxies whose outer stars moved far faster than common sense expected. That is where the mystery sharpened into evidence. Before we get there, it may be nice to pause with one final thought. Not seeing a thing is not the same as being alone with ignorance. Sometimes unseen simply means subtle. Sometimes hidden means waiting for better questions. Sometimes mystery is not a wall, but a doorway that opens when we learn how to notice. And if dark matter really is passing quietly through the room around you tonight, it seems perfectly content to let us rest while it goes about its business, leaving only gravity behind as its calling card. Now that we've settled into the idea that the universe is full of things known by their effects rather than their appearance, we can turn to an important question that sounds simple, but deserves a careful answer. What do scientists actually mean when they say, dark matter? Because the phrase is famous, but fame has a habit of collecting misunderstandings along the way. Some hear the term and imagine black smoke drifting through space. Others picture a sinister substance spreading between stars. A few may suspect it is just a dramatic label for empty space, cosmic dust, or something scientists say when they're confused and hoping nobody asks follow-up questions. the real meaning is more precise, more modest, and in many ways more interesting. When scientists use the phrase dark matter, they mean some form of matter that appears to have mass and therefore exerts gravity, but does not emit, absorb, or reflect light in the ordinary ways that allow telescopes to see familiar objects. That is the key idea. It behaves gravitationally. It hides electromagnetically. Ordinary matter, the kind that makes planets, trees, oceans, sandwiches, and tired people searching for the cool side of the pillow, interacts strongly with light. Atoms absorb certain wavelengths, emit others, scatter photons, glow when heated, reflect sunlight, and leave fingerprints across the electromagnetic spectrum. That is why astronomy works so beautifully. Light carries information. It tells us temperature, composition, speed, distance, motion, and structure. A star may be many trillions of kilometers away, but the light arriving from it is like a detailed letter sent across space. Dark matter, as far as current evidence suggests, does not send that kind of letter. It does not light up as stars do. It does not shine when warmed. It does not seem to form glowing clouds visible in infrared surveys. It does not block starlight the way dust does. It does not announce itself in the normal language of telescopes. And yet, gravity keeps mentioning it. That combination is why the name exists. Dark means invisible to light-based observation, not evil, cursed, or in a bad mood. Matter means it contributes mass and influences motion. It may help to think of the phrase as practical shorthand rather than a final explanation. In science, names often arrive before full understanding. Electrons were named before anyone had a complete quantum theory of them. Atoms were discussed long before their internal structure was known. Black holes were once theoretical oddities before evidence piled high. Likewise, dark matter is a label for a real phenomenon evidenced by gravity, even if the underlying particle or substance remains unidentified. This distinction matters. Dark matter is not merely a guess invented from thin air. It is a placeholder for observed missing mass. Imagine you run a small village bakery. Every morning you weigh flour deliveries, count loaves sold, track ingredients used, and balance the books. 1 week, every measurement consistently shows that far more flour is affecting production than officially entered through the door. You cannot see the extra sacks. No one admits carrying them in. Yet the bread output, dough volume, and oven schedule all insist additional flour is somehow present. You would not know the source yet, but you would know something in the accounting is incomplete. Dark matter plays a similar role in cosmic bookkeeping. The visible ingredients do not fully explain the gravitational results. So scientists ask what unseen mass may be present. Now, an easy confusion appears here. Is dark matter simply regular matter hiding in darkness somewhere? A sensible question, and one researchers considered carefully. Could the missing mass just be faint stars, cold gas clouds, rogue planets, dead stellar remnants, black holes, or dim objects too hard to detect? Some amount of hidden ordinary matter certainly exists. The universe contains faint things. Space is not perfectly catalogued, but detailed measurements, especially from cosmology, show that ordinary matter alone cannot explain the total effect. There simply is not enough baryonic matter, meaning ordinary proton and neutron matter, to account for the gravitational evidence. That conclusion came from multiple lines of data, not one isolated puzzle. Galaxy rotation curves, galaxy cluster dynamics, gravitational lensing, large-scale structure formation, cosmic microwave background measurements. Each points toward more matter than visible atoms provide. When independent clues from very different methods lean the same way, scientists begin paying serious attention. Another misconception is that dark matter equals dark energy. These are separate ideas with famously confusing names. Dark matter seems to pull through gravity and help bind structures together. Dark energy appears related to the accelerated expansion of the universe, acting on cosmic scales in a very different way. One helps explain why galaxies and clusters hold together. The other helps explain why the expansion of space speeds up. Same adjective, different mystery. It is rather like naming two pets Shadow and Shady, and then wondering why visitors seem lost. Let's keep our focus on dark matter itself. If it does not interact with light, how can it be matter at all? Because matter in physics is not defined only by visibility. Matter has mass energy, can influence space-time, and may consist of particles whether or not those particles engage strongly with electromagnetic radiation. Neutrinos are a useful comparison. They are real particles difficult to detect and pass through ordinary matter with astonishing indifference. Trillions pass through you constantly. Their weak interaction does not make them imaginary. Dark matter may be similarly shy, though likely different in mass and behaviour. Some proposed candidates are particles never yet directly detected. WIMPs, axions, sterile neutrinos, and others. Each has its own theoretical motivations and detection strategies. Scientists test these possibilities because dark matter could be a new particle species beyond the standard model of known particles. That would be a major discovery. It would mean the universe contains fundamental ingredients still absent from our current best particle inventory. There is something delightfully humbling in that. Humanity has built colliders, satellites, detectors in mountains, equations of great elegance, and still the cosmos may be saying, "Good start, here is another category you missed." Now, if dark matter is matter, why doesn't it collapse into stars the way ordinary gas does? Excellent question. Ordinary matter loses energy through electromagnetic interactions. Gas clouds radiate heat, cool down, compress, collide, and eventually form stars and planets under gravity. Dark matter appears not to do this efficiently. Without strong electromagnetic interactions, it may not shed energy the same way. So instead of collapsing into bright disks and stars, it tends to remain in broad diffuse halos surrounding galaxies. That is why our Milky Way is thought to sit inside a vast dark matter halo much larger than the visible spiral disk. The stars are like lights in a city. The dark matter is like the hidden terrain and infrastructure shaping where the city can exist. Not a perfect analogy, but a gentle one. There is another subtle point worth noticing. Scientists do not claim to know every property of dark matter with certainty. They infer several things strongly, suspect others, and continue testing the rest. Strongly inferred, it contributes gravity. It is abundant. It clumps on galactic and larger scales. It does not interact with light in ordinary detectable ways. Still uncertain, its exact particle identity, its mass, whether there is one dark matter particle or many types, whether it has weak self-interactions, whether our gravitational theories need modification instead. Science is comfortable with this combination of confidence and uncertainty. That is a strength, not a weakness. Outside science, people sometimes assume you must know everything or nothing. In research, one often knows some features clearly while the deeper mechanism remains open. You may know there is an animal in the attic from sounds, footprints, and missing insulation, long before learning whether it's a squirrel, raccoon, or an entrepreneurially gifted pigeon. Likewise, we know something gravitational is there before knowing precisely what it is. How much of the universe are we talking about? Current cosmological estimates suggest ordinary matter makes up only a minority portion of total matter energy content. Dark matter accounts for far more matter than visible atoms do. Exact percentages depend on how one divides categories, but the central message is consistent. The familiar visible world is not the whole inventory. That realization can sound unsettling if phrased badly. So let's phrase it calmly. It does not mean your chair is secretly dark matter, or that breakfast is mostly mystery particles. Everyday objects are ordinary matter. The visible world around you remains wonderfully real and chemically familiar. It means that on cosmic scales, the universe includes vast additional components beyond what glows. Your room is ordinary matter. The galaxy around it may be embedded in much more. There is also a lovely irony here. For most of history, humans assumed visible things were the main event and darkness was empty background. Modern cosmology suggests the opposite may be closer to truth. The luminous part is the minority accent, while unseen structure does much of the gravitational heavy lifting. Stars are spectacular, but perhaps not numerically dominant. The universe, it seems, enjoys understatement. You may wonder whether dark matter passing through Earth affects daily life. As far as evidence shows, not in any dramatic personal sense. Its interactions with ordinary matter appear so weak that it does not disturb biology, furniture placement, or your chances of finding matching socks. Its importance is structural, cosmic, cumulative. Like foundations beneath a city, it matters enormously without demanding constant attention. This helps explain why dark matter remained unknown so long. Humans evolved to notice immediate practical forces, predators, weather, food, social signals, gravity at human scale. We did not evolve to notice subtle discrepancies in galactic rotation speeds. That required instruments, mathematics, and centuries of curiosity. So when scientists say dark matter, they are not invoking fantasy. They are summarizing a careful conclusion. There exists additional mass in the universe not accounted for by luminous ordinary matter, detected through gravitational effects and still awaiting full identification. That is already extraordinary enough. Long before dark matter became a familiar phrase in documentaries, textbooks, and late-night internet searches that begin with healthy curiosity and end with 17 open tabs, astronomers were noticing that some of the universe's largest systems behaved in ways that did not fit the visible evidence. The stars were moving strangely. Galaxies, those grand collections of stars, gas, dust, and structure, did not seem to follow the simple expectations one would make if only their shining material mattered. Something was off, not wildly, dramatically off in the sense of exploding equations and smoking telescopes, but persistently off in the quiet, stubborn way nature often reveals deeper truths, and quiet inconsistencies can be more powerful than loud surprises. To appreciate why this mattered, let's begin with a gentle thought experiment. Imagine a merry-go-round in a park. Horses fixed to poles circle a centre point. The inner horses travel smaller loops, the outer horses move around larger loops. To complete a turn together, the outer edge must move faster through space than the inner region. You can see this directly. Now imagine our solar system. The planets orbit the Sun, and the farther a planet is from the Sun, the slower it moves in orbital speed. Mercury races around quickly. Neptune glides along much more slowly. Why? Because most of the mass is concentrated in the Sun at the centre. Gravity weakens with distance, so outer planets need less speed to remain in orbit. This became an important intuition for astronomers. If a galaxy's visible mass were concentrated mostly near its centre, then stars far from the centre should orbit more slowly than stars closer in. Not identically to planets in every detail, because galaxies are distributed systems rather than one dominant central object, but broadly speaking, outer regions should show declining orbital speeds once most mass lies inside their orbit. Reasonable, elegant, predictable. The universe, however, had other plans. When astronomers began measuring how fast stars and gas moved in spiral galaxies, especially at large distances from galactic centres, they found something surprising. The outer regions were not slowing down as expected. They were staying fast. In many cases, the orbital speed remained roughly constant far beyond where visible matter suggested it should drop. These measurements created what are called galaxy rotation curves, graphs showing orbital speed versus distance from the centre. Expected curve, rise near the centre, then decline. Observed curve, rise, then flatten. That flattening became one of the strongest clues in modern astrophysics, because if stars far from the centre move quickly and do not fly away, Gravity must be stronger there than visible matter alone predicts, and stronger gravity means more mass. Mass that was not being seen. Before we focus on the famous later measurements, it is worth meeting one of the early thinkers who noticed missing mass on even larger scales, Fritz Zwicky. In the 1930s, Zwicky studied the Coma cluster, a massive cluster of galaxies bound together by gravity. By measuring how fast the galaxies moved within the cluster, he estimated how much mass would be needed to keep the cluster from dispersing. The visible galaxies did not provide enough, not even close. He concluded there must be unseen matter present, which he referred to as Dunkelmaterie, German for dark matter. Now, Zwicky was brilliant, bold, and famously not known for timid opinions. Some of his ideas were ahead of their time. Some colleagues found him challenging in the way thunderstorms can be considered lively weather. As a result, not all of his conclusions were immediately embraced. Still, history has a fondness for data that refuses to disappear. His central concern returned again and again. Systems seemed heavier than they looked. Yet it was later work on spiral galaxies that made the case especially compelling. Enter Vera Rubin, whose careful observations in the 20th century became central to the dark matter story. Along with collaborators including Kent Ford, Rubin measured the motions of stars and gas in spiral galaxies with increasing precision. What she found helped transform a puzzling suspicion into a major scientific conclusion. Instead of tapering downward, many galaxy rotation curves stayed unexpectedly flat at large radii. Let's make this intuitive. Imagine a city at night seen from above. Most lights are concentrated downtown. If brightness represented mass, you would assume the outer suburbs contribute less and less to the city's gravitational pull. Yet when measuring traffic speeds on roads farther and farther out, you discover cars that are somehow moving as though a vast hidden metropolis extends beyond the visible lights. That would be strange. You would suspect one of two things. Either your understanding of traffic laws is incomplete, or there is more city than you can see. Astronomers faced a similar fork. Either gravity behaved differently on galactic scales, or there was additional unseen mass. Both ideas were taken seriously. Both are still discussed in different forms today. But dark matter became the leading explanation because it fit multiple lines of evidence, not rotation curves alone. Still, the galaxy evidence was emotionally powerful because it was so direct. You look at a galaxy, you measure visible matter, you measure orbital speeds. They do not match. The stars, in effect, were voting with their motion. Now, one might ask, how do astronomers know how fast stars or gas are moving in distant galaxies? A lovely question. They use light, specifically the Doppler effect. If something moves toward us, its light shifts slightly toward shorter wavelengths. If it moves away, the light shifts toward longer wavelengths. By measuring these shifts across different parts of a rotating galaxy, astronomers determine which side is approaching, which is receding, and how fast material is orbiting. So even though we cannot travel there with a cosmic speedometer and politely ask the stars to slow down for inspection, light carries the needed information. Again, the universe communicates generously if one learns the language. The result was unsettling in the best scientific sense. Outer stars should have been slower if visible matter dominated. They were not. To keep those fast outer orbits stable, galaxies seemed wrapped in much more mass than their luminous disks contained. Hence the idea of dark matter halos. A spiral galaxy like our Milky Way is not just a shining disk of stars and gas. It is thought to sit inside a much larger, roughly spherical halo of dark matter, extending far beyond the visible spiral arms. The bright galaxy is the part we notice. The halo is the part doing much of the gravitational anchoring. There is something almost humorous in that arrangement. Humans adore the lights, photograph the lights, write songs about the lights, and it may be the invisible scaffolding doing the heavier labour. Very on brand for the universe. Now, it is worth remembering how radical this sounded. Science had already revealed many invisible phenomena, yes, But proposing that galaxies contain far more unseen matter than visible matter was not a small bookkeeping adjustment. It implied that what shines may be only a fraction of what exists. That challenges intuition. We naturally trust what glows. Stars feel substantial. Nebulae feel grand. Brightness suggests importance, but brightness and abundance are not the same thing. A candle in a dark room dominates vision, while contributing very little mass compared with the furniture. Likewise, luminous matter dominates astronomical imagery, while possibly representing only a minority share of matter overall. Another reason these clues mattered is that they appeared across many galaxies, not just one oddball system having a strange day. Different sizes, different shapes, different environments. Again and again, flat rotation curves emerged. When nature repeats a pattern broadly, scientists listen more carefully. Could the missing mass have been ordinary but dim matter? Faint stars, gas, black objects. Some of it perhaps, but not enough. Detailed observations across wavelengths and later cosmological evidence narrowed that option considerably. The mystery deepened rather than faded. There is a quiet beauty in how this happened. No monster leapt from a crater, no hidden chamber opened under a pyramid, no dramatic beam shot from the sky. Instead, people measured spectra, plotted graphs, checked uncertainties, refined instruments, and noticed curves that refused to bend downward. That is how many revolutions actually begin, with patient disagreement between expectation and measurement. And disagreement in science is precious. It means reality is still teaching. Imagine if every result matched old assumptions perfectly forever. Comforting perhaps, but sterile. Discovery often starts when nature says no. No, galaxies do not rotate as simply as you thought. No, visible matter is not the whole story. No, your first model was not final. Such refusals have given us relativity, quantum theory, plate tectonics, and much else besides. Dark matter joined that lineage through motion. You might also wonder whether our own galaxy behaves this way. Yes. Measurements of stars, gas clouds, and satellite motions suggest the Milky Way also resides in a substantial dark matter halo. In fact, estimates of dark matter density near the solar system help guide direct detection experiments here on Earth, so the strange behaviour was not happening elsewhere while we remained exempt. Our galactic home appears part of the same pattern. There is comfort in that too. Mystery is evenly distributed. The more astronomers studied galaxies, the more the visible universe began to resemble a theatre set, whose painted front wall concealed vast support beams behind it. The scene remained real and beautiful, but incomplete if judged only from what was lit. Once astronomers realized that individual galaxies seemed to contain more mass than their stars and gas could explain, a larger and even more intriguing question emerged. What if this was not merely a galactic quirk? What if the whole universe, across many scales, consistently weighed more than it appeared to? That possibility shifted the mystery from local oddity to cosmic pattern. It was one thing for a spiral galaxy to rotate strangely. Perhaps some hidden gas had been missed. Perhaps measurements needed refinement. Perhaps galaxies were more complicated than simple models suggested. All true to a degree. But when galaxy clusters, large cosmic structures, and independent methods began telling the same story, the missing mass problem stopped looking like a bookkeeping error and started looking like one of nature's main plot points. To understand why, let us begin with the simple human act of lifting things. If you pick up an empty suitcase, you form an expectation. If it rises easily, no surprise. If it nearly pulls your shoulder from its socket, you instantly know something substantial is inside. You may not know whether it contains books, bricks, bowling balls, or a relative's deeply committed vacation wardrobe, but the weight tells you appearance was misleading. Astronomy often works the same way. The universe cannot be placed on a bathroom scale, which is just as well because the reading would be discouragingly large. Instead, astronomers infer weight through gravity. They observe how fast objects move, how tightly systems stay bound, how light bends, and how structures grow over time. Mass reveals itself by influence, and once scientists became good at reading those influences, many cosmic systems turned out to be unexpectedly heavy. Let's return for a moment to galaxy clusters, those immense gatherings of hundreds or even thousands of galaxies bound together by gravity. These are among the largest structures in the universe held together as coherent systems. Picture not one city, but an entire continent of cities moving within a shared landscape. In the 1930s, Fritz Zwicky studied the Coma cluster and measured the speeds of galaxies moving inside it. If the cluster contained only the visible mass of its galaxies, those galaxies were moving too fast to remain bound. They should have escaped, yet they had not. That meant either gravity behaved very differently there, or far more mass existed than telescopes could see. Zwicky estimated the cluster might contain vastly more matter than luminous material suggested. At the time, this was startling and not universally embraced. Science is often cautious with bold claims, especially when they imply the cosmos has hidden most of its ingredients in the pantry. Still, the problem did not go away. Later observations improved instruments, refined techniques, and found similar discrepancies in many clusters. The universe kept arriving heavier than advertised. Now, galaxy clusters offer more than moving galaxies. They also contain enormous amounts of hot gas filling the space between galaxies. This gas is so hot that it emits X-rays rather than visible light. Once X-ray astronomy matured, scientists could detect and map this glowing intracluster gas. For a while, this seemed promising. Perhaps the missing mass was simply hot gas overlooked by optical telescopes, and indeed, the gas contributes a great deal of ordinary matter. In many clusters, it outweighs the stars within galaxies. That was an important discovery. But even after accounting for the gas, there was still not enough mass to explain the observed gravity. The suitcase remained suspiciously heavy. This is one of the most elegant features of the dark matter case. The mystery survived improved data. It was not created by ignorance alone. As astronomy learned more, the discrepancy persisted in updated form. That is often how robust scientific puzzles behave. You solve the first version, only to discover a deeper version waiting politely underneath. Then came another powerful tool, gravitational lensing. According to Albert Einstein's general relativity, mass curves space-time and light travelling near mass follows that curvature. In practice, massive objects can bend and distort light from more distant sources behind them. Galaxy clusters act like gigantic lenses. When astronomers observe stretched arcs, duplicated images, or distorted background galaxies around clusters, they can estimate how much total mass is present from the lensing strength. And once again, visible matter alone fell short. The lensing maps often revealed much more mass than stars and gas could account for. Now the evidence came from motion and from bent light. Different methods, same message. There is something deeply convincing when independent tools agree. If one thermometer says it is cold, perhaps it is faulty. If thermometers, frost on the window, and your regrettable decision to go outside in slippers all agree, confidence rises. Likewise, galaxy motions, X-ray gas studies, and gravitational lensing converged. The universe seemed massively underlit. A particularly famous example is the Bullet cluster. This system consists of two galaxy clusters that collided. During the collision, the hot gas from each cluster interacted strongly, slowed down and piled up. The galaxies themselves, being mostly empty space relative to their size, passed through more easily. Here is where it becomes fascinating. When astronomers mapped the ordinary matter using X-rays, most of it sat with the slowed gas. But when they mapped total mass using gravitational lensing, much of the mass appeared offset, following the galaxies rather than the gas. In simple terms, the visible ordinary matter and the main gravitational mass had separated. This became powerful evidence that a large component of matter existed which did not behave like ordinary gas. It moved through the collision differently. Not everyone interprets every system identically, and scientific debate continues in details, as it should. But the bullet cluster became one of the clearest visual cases that unseen mass is not merely missing light from normal matter. Something else appears present. Now, step back from clusters and consider the universe as a whole. Modern cosmology studies the composition of the cosmos using multiple observations, including the cosmic microwave background, the afterglow of the early universe. Tiny temperature fluctuations in this ancient radiation encode information about matter density, geometry, and cosmic evolution. It is one of science's most impressive records, a baby picture of the universe containing subtle clues about adulthood. When satellites such as NASA's WMAP and later European Space Agency's Planck spacecraft measured these patterns in extraordinary detail, the inferred cosmic composition again indicated that ordinary matter is only a minority component. Dark matter contributes much more matter than atoms alone. Notice the pattern now. Galaxies rotate too fast. Clusters are too tightly bound. Lensing reveals extra mass. Early universe radiation implies additional matter. Large-scale structure formation works better with invisible mass present. At some point, repeated agreement stops being coincidence. It becomes diagnosis. You may wonder why visible matter alone struggles to form today's universe. In the early cosmos, ordinary matter interacted strongly with radiation. That coupling smoothed out density clumps. Dark matter, if it interacts weakly, could begin forming gravitational wells earlier. Ordinary matter later fell into those wells after the universe cooled enough for atoms to form and light to travel freely. In that picture, dark matter acts like early scaffolding. Not glamorous perhaps, but indispensable. Much of reality depends on things willing to do structural work without seeking credit. Beams inside walls, roots beneath trees, foundations under cities, possibly dark matter beneath galaxies in a gravitational sense. There is also an emotional side to this discovery worth noticing. Humans once assumed that what was bright and visible dominated the cosmos. Stars seem majestic, nebulae glow beautifully, galaxies shine in photographs like celestial jewellery. Yet the more we measured, the more we learned that brightness is not the same as abundance. The visible universe may be the decorative surface of a deeper mass budget. This is not disappointing, it is enriching. Nature often hides scale behind appearances. A mountain's visible summit may be smaller than what lies underground. An iceberg reveals little of itself above water. A forest's life depends as much on soil networks and roots as on trunks and leaves. Likewise, cosmic light may reveal only part of cosmic substance. Another question naturally arises. If the universe contains so much unseen matter, why did it take us so long to notice? Because at human scales, ordinary matter dominates experience. You touch tables, breathe air, drink water, trip over shoes left in hallways, and negotiate daily life with atoms that readily interact. Dark matter appears reluctant to do any of that. Its gravitational influence becomes especially obvious on large scales where huge amounts accumulate. Galaxies, clusters, and cosmic history are where it speaks loudest. A single grain of sand is easy to ignore on a beach. Entire dunes shape landscapes. Similarly, a faint local density of dark matter may be subtle. Vast halos and cluster masses are another matter entirely. There is humility in this lesson. Our senses are local specialists, not universal auditors. We evolved to detect food, danger, faces, weather, and social cues. We did not evolve to estimate cluster mass from galaxy velocity dispersion. So we built mathematics, telescopes, detectors, and patient methods to extend ourselves. And what they found was a universe heavier than it looked. Not by a tiny rounding error, by enough to transform cosmology. That does not mean every question is settled. Scientists still debate particle candidates, test alternatives to gravity, refine simulations, and chase direct detection signals. The identity of dark matter remains unresolved, but the evidence that something substantial is missing from the visible inventory is strong and multi-layered. We know the suitcase is heavy. We're still investigating what is packed inside. After learning that galaxies rotate too quickly, clusters weigh too much, and light bends around mass we cannot fully see, a natural response often follows. All right then, how much of the universe are we talking about? Is dark matter a modest correction, the cosmic equivalent of discovering a few forgotten coins beneath the sofa cushions? Or is it something larger? The answer is one of the most perspective-shifting discoveries in modern science. It is much larger. When astronomers and cosmologists add together the best available evidence from galaxy motion, gravitational lensing, the cosmic microwave background, large-scale structure, supernova measurements, and other observations, they arrive at a universe whose composition is very different from what human intuition once imagined. The stars are not the main ingredient, neither are planets, neither are clouds of gas, oceans, mountains, people, teacups, or all the visible furniture of existence combined. Instead, the cosmos appears to be made mostly of components that remain mysterious. That sentence deserves a slow moment. For thousands of years, people looked up at the night sky and naturally assumed the shining things were the story. Bright objects attract attention. They seem important. If the heavens were a theatre, the stars looked like the cast. Modern cosmology suggests many of them are more like the lighting. Beautiful, essential, informative, but not the majority of the total budget. According to current models, only a relatively small fraction of the universe consists of ordinary matter, the familiar atoms built from protons, neutrons, and electrons. This ordinary matter forms stars, dust, planets, bodies, bookshelves, bread, and every dramatic search for missing phone chargers. Dark matter contributes a much larger share of matter than ordinary atoms do, and beyond both lies another even stranger component called dark energy, associated with the accelerated expansion of the universe. The exact percentages are refined as measurements improve, but the broad modern picture is often summarized roughly like this. A small minority is ordinary matter. A larger portion is dark matter. The largest share is dark energy, which means the everyday visible world, rich and detailed though it is, may represent only a thin slice of the total cosmic inventory. That realization can land in several ways. For some, it feels unsettling. For others, thrilling. Personally, I think it is wonderfully humbling, because it reminds us that reality is under no obligation to match first impressions. Consider how often this has happened before. Ancient people saw the sun move across the sky and assumed Earth stood still, reasonable from the ground. Later we learned Earth rotates and orbits the sun. Then we learned the sun is one star among many. Then that our galaxy is one among billions. Then that visible matter itself may be only a minority component of the whole. Again and again, knowledge has not diminished reality. It has expanded it. There is comfort in that pattern. Surprise need not be threatening. It can be generous. Now, when scientists say most of the universe is unknown, they do not mean nothing is known. Quite the opposite. We know a great deal about how these components behave at large scales. We know dark matter gravitates. We know it helps structure galaxies and clusters. We know dark energy is consistent with cosmic acceleration. We know ordinary matter forms the visible complexity around us. What remains uncertain is the deeper identity and mechanism. Think of it this way. You may know someone is in the kitchen because you hear cupboards opening, pans moving, and a spoon falling with theatrical commitment. You know activity is happening even before seeing who it is. Likewise, cosmologists infer hidden components through effects. The universe leaves footprints. One useful distinction here is between familiarity and abundance. Ordinary matter is familiar because it interacts strongly with us. We are made of it. We sense it constantly. It forms the textures of daily life, so it feels central. But feeling central is not the same as being numerically dominant. A candle in a dark hall dominates vision while containing little of the building's total mass. The visible can be vivid without being most of the whole. That may be true of stars. Indeed, stars are spectacularly efficient attention magnets. They glow across darkness, mark seasons, guide navigation, inspire poetry, power planets, and generally behave like celestial celebrities. Dark matter, by contrast, does not shine, does not twinkle, and appears uninterested in public relations. Yet it may outweigh stars many times over. The universe, it seems, does not always reward showmanship. Now let us bring this down from cosmic scales to a more human one. If only a small fraction of the universe is ordinary matter, does that mean your body is mostly dark matter? No. Thankfully, no surprise identity crisis is required tonight. You, your bed, your room, your house, and the visible objects around you are made overwhelmingly of ordinary matter. Dark matter does not replace atoms in your bones or tea in your mug. The cosmic percentages describe the universe overall, not the composition of everyday household items. That distinction matters. Imagine a planet covered mostly by ocean, with islands scattered across it. A person standing on an island is not made mostly of seawater, even though seawater dominates the planet's surface. Likewise, we inhabit regions rich in ordinary matter, because ordinary matter clumps into stars, planets, chemistry, and biology. Dark matter behaves differently, distributing itself in large halos and structures, rather than becoming dinner plates and garden sheds. So while the cosmos overall may be mostly unknown components, your pillow remains reassuringly ordinary. Another elegant question follows. If ordinary matter is the minority, why does it produce so much complexity? Because ordinary matter is socially active, in a physical sense. It interacts electromagnetically. It forms atoms, molecules, chemistry, liquids, solids, crystals, cells, brains, weather systems, forests, coral reefs, violins, and mildly overcomplicated coffee machines. Dark matter appears comparatively reserved. It shapes through gravity but does not seem to join chemistry class. So the visible minority may create the rich detail of life precisely because it has the right kinds of interactions. Sometimes small fractions matter immensely. A tiny amount of yeast transforms dough. A modest electrical current runs a city's systems. A few notes arranged well become music. Likewise, ordinary matter may be a minority ingredient while still generating extraordinary complexity. There is something reassuring in that too. Importance and abundance are not identical. Now let's talk briefly about how we know these proportions at all. One of the strongest tools is the cosmic microwave background. Faint radiation left from the early universe when atoms first formed and light began travelling freely. Tiny fluctuations in this background encode information about density, expansion, geometry, and composition. It is astonishing that by measuring delicate temperature variations across the sky, scientists can infer what the universe contains. That is like learning the ingredients of a cake by studying how it cooled. Yet physics allows precisely such detective work. Additional clues come from how galaxies cluster over time, how light bends around massive structures, and how the universe expands today. Different methods, different eras, different physical processes, converging conclusions. That convergence is one reason modern cosmology treats this composition seriously. Still, it remains healthy science to ask questions. Could some assumptions be revised? Could gravity need modification? Could dark matter consist of multiple components? Could dark energy be more subtle than a simple constant? Yes to all as legitimate areas of inquiry. Science is not frozen certainty. It is structured curiosity. But within that curiosity, some broad results are strongly supported. The visible universe is not the whole universe. There is also a psychological side to this discovery. Humans often crave completion. We like maps with clear borders, inventories with every shelf labelled, stories with tidy endings. Yet one of the most successful scientific eras in history has arrived at a remarkable admission. We understand many laws beautifully. We can predict countless phenomena. We can send probes across the solar system. We can model cosmic history. And still, most of the universe involves components whose deepest nature is not yet fully known. That is not failure. That is progress honest enough to state its frontier. There is dignity in saying, here is what we know, here is what we infer, and here is what remains mysterious. Too often, people imagine science as a machine that only outputs certainty. In reality, science is also the art of measuring mystery carefully, and what a mystery this is. A universe where stars are not the main mass, a cosmos where invisible matter shapes galaxies, an expanding space driven by something still debated and explored, a reality larger than appearances. You may wonder whether future generations will look back on our era as the time when humanity knew dark matter's identity, but had not yet confirmed it, much as earlier ages knew electricity's effects before electrons were understood. That is entirely possible. We may be living in the before phase of an explanation that later students treat as standard. Or perhaps the answer will prove stranger than our current categories. History offers both possibilities. There is another comforting thought tucked inside all this. Even if most of the universe is mysterious, daily life need not be. You do not need to solve cosmology to sleep well, love well, eat breakfast, or appreciate rain on a window. The unknown can remain vast without making the known any less real. Your room is still your room. Your breath still rises and falls. The floor still trusts gravity completely. The stars still shine whether or not we have completed the inventory. And perhaps that balance is healthy. Enough understanding to live confidently, enough mystery to stay curious. If dark matter is spread through halos around galaxies, and if our Milky Way lives inside one, then what does that mean for the place where you are right now? Is some of this invisible matter actually around you, here tonight, quietly passing through your little corner of the universe at this very moment? After wandering through galaxy clusters, cosmic inventories, invisible halos, and the surprising realization that much of the universe may be made of components we do not directly see, we arrive at a question that feels wonderfully personal. What about here? Not somewhere near a distant quasar, not at the center of a galaxy billions of light years away, not in an equation on a whiteboard, nor inside a detector buried under mountains, right here, right now. In the room where you're listening, in the building around you, above the roof, beneath the floorboards, beyond the walls, through the air, through the earth itself. Is dark matter actually around you? According to our best current scientific understanding, yes, very likely it is. That answer may sound dramatic at first, but the reality is far calmer than the phrase suggests. Dark matter is not gathering in corners. It is not pooling under the bed like cosmic fog. It is not pressing against windows hoping to be noticed. Instead, the idea comes from something much larger and quieter. Our Milky Way appears to sit inside an extended halo of dark matter, a vast, roughly spherical distribution of unseen mass stretching far beyond the visible spiral disk. Stars, gas clouds, star clusters, and our own solar system move within that larger halo. That means the Earth is not outside it. The Earth is inside it. The Sun is inside it. You, rather impressively, are inside it too. This is one of those scientific facts that sounds like a line from fiction, but is actually a consequence of ordinary orbital mechanics and mass models. We do not inhabit an isolated bright island floating in emptiness. We inhabit a luminous region embedded within a much larger invisible gravitational environment. Think of a city built within a valley. Many residents may spend their days focused on streets, houses, traffic lights, bakeries, parks, and whether parking regulations are fair to anyone at all. Yet the valley shape surrounding hills and underlying terrain quietly influence weather, drainage, roads, and where the city developed in the first place. Dark matter is something like that hidden terrain on galactic scales. You may not notice it directly while making tea or adjusting blankets, but it helps define the larger environment in which our galaxy exists. Now, if you are imagining dense streams of exotic particles thundering through the room like invisible weather, let us slow that picture down. The local density of dark matter near our solar system is believed to be quite low in everyday terms. Even though it matters enormously on galactic scales, it is spread out enough that a room full of ordinary objects contains overwhelmingly more ordinary matter by local density than dark matter. Your bookshelf wins the immediate mass contest. So does the wall, probably the rug as well. Dark matter is significant because of total amounts across huge volumes, not because your bedroom has suddenly become a storage unit for invisible cosmic substance. This distinction is important and calming. A mist across an entire valley can contain much water overall while leaving only a light touch in any single cubic meter of air. Scale changes meaning. Likewise, dark matter spread across galactic dimensions becomes enormous in total mass. Locally, it remains subtle. Still, subtle does not mean absent. If standard models are correct, dark matter particles should be moving through the region around Earth continuously. As the solar system orbits the Milky Way, and as our galaxy moves through space, we travel through this dark matter halo much as a ship moves through a calm sea. Except the sea is invisible and mostly uninterested in ships. That image helps explain why scientists on Earth build detectors searching for tiny interactions. If dark matter surrounds us, perhaps now and then a particle might bump into ordinary matter in a measurable way. Most likely, if such particles exist, those interactions are extremely rare, hence the patience, and the underground laboratories, and the very sensitive instruments protected from ordinary background noise by rock, shielding, and careful design. Humans have always had a talent for elaborate arrangements in pursuit of answers. Sometimes we build cathedrals, sometimes particle detectors under mountains. Both involve hope, precision, and impressive architecture. Let's bring this back to the listener for a moment. Wherever you are tonight, perhaps you are in Wroclaw, perhaps elsewhere entirely. Maybe you are in a tower apartment, a countryside house, a student room, a hotel, a train carriage, or resting on a sofa with one blanket that somehow became three through excellent planning. Dark matter, if present as expected, does not care much about these distinctions. Brick walls are ordinary matter, wood beams are ordinary matter, steel frames, glass panes, tiled roofs, socks abandoned on stairs, all ordinary matter. Dark matter likely passes through such barriers with little concern because it seems to interact so weakly with atoms. That can sound uncanny until one remembers how many familiar things also ignore walls in their own way. Radio signals pass through buildings, neutrinos pass through the Earth, magnetic fields reach across space. Sunlight crosses 93 million miles to warm your face. The universe is full of traffic that does not request permission from architecture. Dark matter would simply be another member of that quiet category. You may ask a very practical question. If it is around me, does it affect me? In the immediate personal sense, no evidence suggests any noticeable daily effect. It does not alter mood, cause fatigue, improve Wi-Fi, wrinkle curtains, reorganize furniture, or explain where missing teaspoons go. Its influence is gravitational and cumulative, not dramatic and household scale. This is worth emphasizing because hidden things are often blamed for too much. If you forgot your keys, dark matter was almost certainly not involved. If your toast burned, responsibility lies closer to the toaster. If you stayed awake scrolling far longer than planned, dark matter once again appears innocent. Its role is grander and less personal. It helps shape galaxies. It contributes to the gravitational environment of large systems. It likely played a major role in structure formation early in cosmic history. That is already plenty to be getting on with. There is another angle to this question that I find especially soothing. To ask whether dark matter is around you is to remember that your life is not separate from the universe. We often divide experience into two categories: everyday life here, cosmic reality out there. But there is no true border. The atoms in your body were forged in ancient stars. The oxygen you breathe was made in stellar interiors. The Earth orbits within a galaxy. The galaxy sits in a larger halo. The cosmic story is not elsewhere. It includes your address. You're not standing outside astronomy looking in. You're one local event inside it. Even listening quietly at night becomes a cosmic activity when viewed honestly. A human nervous system built from star-made elements rests on a planet circling one star among hundreds of billions, inside a galaxy moving through a universe whose hidden matter may stream gently through the room, and yet the moment can remain wonderfully simple. You breathe in, you breathe out. The blanket is warm, the room is dim. Mystery does not need to be noisy. Sometimes people hear facts like this and ask, how can something be real if I cannot sense it? A fair question, though our lives already answer it repeatedly. You do not sense the Earth's orbital motion directly, yet it races around the Sun. You do not feel every cell dividing, yet biology proceeds. You do not hear most frequencies around you. You do not see air molecules, bacteria, ultraviolet light, or radio waves unaided. Human senses are local tools, not total judges. Science extends them. And one of the gifts of science is the ability to inhabit a richer world than instinct alone provides. Without it, a night sky is lights. With it, a night sky is stars, planets, galaxies, nuclear furnaces, space-time, ancient photons, orbiting worlds, and perhaps vast halos of invisible matter. The same sky, deeper meaning. The same room, larger context. There is also a delightful modesty in how dark matter presents itself. It may be everywhere around us, yet it does not demand centre stage. It does not sparkle. It does not roar. It leaves gravity as its calling card and otherwise minds its own business. A lesson many public figures might consider. Now, scientists estimate a local dark matter density near the solar system based on stellar motions and galactic models. These estimates help determine how often particles might pass through detectors and what signals experiments should seek. The numbers are technical, refined, and updated over time, but the broad conclusion remains. Our region of the Milky Way is expected to contain dark matter as part of the galactic halo. So yes, not just somewhere abstractly. Here, near Earth, around the solar system, through this neighbourhood of space, perhaps even through the small patch of air between your hands if they are resting together now. And because it interacts so weakly, you would never know by sensation alone. There is something oddly comforting about that. The universe can contain immense hidden realities without disrupting the gentleness of a quiet evening. Mystery and normality coexist perfectly well. If dark matter may be around you right now, perhaps even passing through the room, through the walls, through the earth, and through you without so much as a polite knock, then the next question arrives almost immediately. Why can't you feel it? Why no sensation at all? No shiver, no pressure, no faint buzz, no mysterious cosmic tap on the shoulder, as if the universe were checking whether you're still awake? The short answer is this: because feeling requires interaction, and dark matter, as far as current evidence suggests, interacts with ordinary matter either extremely weakly or in ways we have not yet directly detected, aside from gravity. That one idea explains nearly everything about its strange invisibility in daily life. To feel something, your body needs signals. Touch happens when pressure deforms skin and activates nerve endings. Heat is sensed when temperature changes affect specialized receptors. Sound arrives as vibrating air moving the structures of the ear. Pain warns of tissue damage or chemical stress. Even the sense of balance depends on fluid motion in the inner ear. All of these experiences rely on matter interacting with matter in clear, energetic ways. Something pushes, vibrates, heats, stretches, collides, or chemically alters tissue. Your nervous system notices. Dark matter appears to be exceptionally poor at doing that. It may pass through ordinary atoms with barely any interaction at all. If so, then there is no meaningful push on skin, no warming of tissue, no vibration of nerves, no chemical trigger, and no sensory message sent to the brain. Nothing to feel. This may seem counterintuitive because we often imagine matter as solid stuff that must bump into other stuff dramatically. Yet even ordinary matter is stranger and emptier than intuition suggests. Let us slow down and visit the atom. Atoms, the building blocks of familiar matter, consist of a tiny dense nucleus surrounded by electrons occupying regions of probability. If the nucleus was scaled to something like a pea at the centre of a stadium, the rest of the atom would be mostly space-defined by fields and quantum structure. Matter feels solid not because atoms are little billiard balls packed tightly edge to edge, but because electromagnetic forces resist overlap and motion at close range. When your hand presses against a table, the sensation of solidity comes largely from electromagnetic repulsion between atoms in your skin and atoms in the table. You do not touch the table in the simple cartoon sense. You experience force interactions between electron clouds and atomic structures. That means even familiar touch is already a story about invisible forces, rather than tiny hard marbles clacking together. Dark matter seems not to participate much in those electromagnetic interactions. So while ordinary matter strongly resists ordinary matter at close distances, dark matter may simply pass through atomic structures with only a minuscule chance of interacting. The table feels solid to your hand. The table may be nearly irrelevant to dark matter. Likewise, your body feels solid to itself because of ordinary forces. But to a dark matter particle, if current models are right, your atoms may be mostly navigable terrain. That sounds dramatic, though it is really just particle physics behaving consistently. We already know of particles that ignore matter impressively well. Consider neutrinos. These tiny particles are produced in enormous numbers by the sun, nuclear reactions, cosmic rays, and other energetic processes. Trillions pass through your body every second. Most continue onward through the earth as if it were barely there. You do not feel them. You do not notice them during breakfast. They do not interrupt naps, and yet they are real, measurable, and scientifically important. Dark matter, if particle-like, may belong to a similar family of elusive travellers, though likely with different properties. This is why dark matter experiments require extraordinary sensitivity. Imagine trying to detect one soft footstep in a stadium during a thunderstorm while everyone else is also opening snack wrappers. That is roughly the challenge. Earth is bathed in ordinary background signals, cosmic rays, natural radioactivity, thermal noise, electronic noise, environmental vibrations, and the endless enthusiasm of particles doing particle things. To search for a rare dark matter interaction, scientists build detectors deep underground where rock shields many unwanted signals. These experiments often sit in mines, tunnels, or laboratories beneath mountains, not because dark matter prefers dramatic locations, but because ordinary noise is the real nuisance. The hidden lesson here is lovely. The problem is not that dark matter is too active to handle, it is that it may be too quiet to hear. Now, let us address a common intuition. If countless particles are passing through me, shouldn't many tiny effects add up to something noticeable? Reasonable thought. But notice how scale and interaction probability work together. Rain hitting you is noticeable because droplets collide strongly and transfer momentum. Wind is noticeable because huge numbers of air molecules constantly strike your skin. Warm sunlight is noticeable because photons are absorbed and transfer energy. In each case, Interactions are common enough and energetic enough to matter biologically. Dark matter appears different on both counts. Individual interactions, if they occur, may be extremely rare or extremely weak. Even many particles passing through does not guarantee noticeable sensation if almost none deposit meaningful energy. A crowd whispering from miles away remains silent to you. Number alone is not enough. There is another comforting angle to this. Your body is not a passive object helpless before invisible particles. It is a remarkably stable biological system built to function amid countless unseen processes already happening around and through it. Electromagnetic radiation from the environment, neutrinos from the sun, air molecules colliding constantly, microbial life everywhere, gravity from the moon tugging oceans, and in tiny ways you, Earth rushing through space, cells replacing cells. You're already living inside layers of invisible activity. Dark matter, if present locally, would simply join a crowded list of things your body handles by not needing to care. That may be one of the great underappreciated skills of biology: selective ignorance. Your nervous system does not report every molecule strike, every photon, every subtle fluctuation, every cellular adjustment. If it did, consciousness would be unusable. Instead, the brain filters fiercely. It highlights what matters for survival and behaviour. Pressure on the foot, pain in the hand, a sudden sound behind you, the smell of smoke, the approach of breakfast. This means even if some tiny dark matter interactions occurred occasionally, they would need to be both biologically significant and detectable by sensory systems designed for them. There is no reason to assume either is true. Evolution did not shape humans to sense galactic halo particles. It shaped us to avoid cliffs and appreciate ripe fruit. Quite practical priorities. Sometimes people ask whether dark matter passing through the brain could influence thoughts or dreams. Current evidence gives no reason to think so. The interactions appear too weak and too rare for anything like that in ordinary conditions. If your thoughts feel strange at midnight, the explanation is far more likely to involve fatigue, stress, memory, caffeine, or that one conversation you unexpectedly replay from 6 years ago. Dark matter again appears innocent. Another useful perspective comes from scale. Suppose a single dark matter particle did interact in some detector. That event might involve an energy deposit tiny enough to require sophisticated instrumentation, cryogenic temperatures, ultra-pure materials, and careful statistical analysis. Compared with that sensitivity, human senses are wonderfully useful but not precision particle observatories. Your fingertips are excellent for fabrics. Your ears are superb for voices. Your nose can detect certain smells at astonishingly low concentrations. But none of these systems were designed to register rare subatomic recoil events from hypothetical, weakly interacting particles. One should not criticize them for this. A spoon is also poor at astronomy, yet remains valuable. There is also the matter of gravity itself. Could you feel dark matter through gravitational pull? In principle, gravity from any mass exists. In practice, local dark matter density is low enough that nearby ordinary objects dominate the gravitational effects relevant to your senses. The Earth beneath you contributes vastly more noticeable gravity than diffuse dark matter in the room. Your bed matters more to your current comfort than a galactic halo, as beds should. Dark matter's gravitational significance emerges over huge scales: galaxies, clusters, cosmic structure. There, cumulative mass across vast regions becomes important. At bedroom scale, it is subtle. That contrast is common in physics. A single snowflake is delicate. A mountain snowpack shapes landscapes. One drop of water is trivial. An ocean commands weather. Likewise, sparse local dark matter is negligible to sensation, while immense total dark matter distributions guide galaxies. You might find it soothing that the universe often separates drama by scale. What matters cosmically need not disturb your pillow. There is something philosophically rich here too. Much of reality is not hidden because it is secretive, but because our senses are specialized. We perceive the slice of the world useful for human life, not the total inventory. Dogs smell realms we miss. Birds navigate cues we barely understand. Instruments detect wavelengths invisible to eyes. Equations reveal patterns senses never would. Dark matter may be another reminder that being unable to feel a thing says more about us than about the thing, and that is not a flaw. No creature perceives everything. Knowledge grows by extending perception thoughtfully. So when you ask, why can't I feel dark matter passing through me? The answer is not that you're missing something obvious. It is that sensation depends on interaction, and dark matter seems remarkably reluctant to interact in ways nerves can notice. No push, no heat, no sound, no signal worth reporting. Just a quiet passage through ordinary matter, if our models are right. Once we accept the strange possibility that dark matter may be present around us while interacting so weakly that our bodies never notice it, another question naturally steps forward. How much of it are we talking about? Is the region around you visited by the occasional lonely particle drifting past like a single leaf on a pond? Or is something far busier taking place, hidden behind the calm appearance of an ordinary room? The answer, depending on what dark matter actually is, may be astonishing. There could be vast numbers of particles moving through your body and surroundings every second, quietly and continuously, while daily life proceeds without interruption. No drama, no sound, no sensation, just motion. Now, we must begin with an important note of scientific honesty. We do not yet know the exact identity of dark matter. Because of that, we do not know the exact mass of its particles, and because the number of particles depends on particle mass, estimates vary enormously depending on which candidate is real. If dark matter particles are relatively heavy, fewer would be needed to make up the local mass density. If they are extremely light, many more would be required. Same total mass, different particle counts. Think of the difference between a room containing bowling balls and a room containing grains of sand. The total weight could be similar while the number of objects differs wildly. Dark matter may present a similar situation, so when people say billions of particles may be passing through you, that can be a plausible image under some models, while other models imply far fewer or vastly more. The key point is not one exact number. The key point is continuous flux. Something may be streaming through our region of space all the time. To understand why, let us return to our place inside the Milky Way. Our solar system orbits the galactic center at great speed. The galaxy itself moves through space. Meanwhile, the Earth orbits the Sun and rotates daily. We are not stationary observers sitting in a quiet cosmic room. We are travelers inside a moving system. And if the Milky Way is embedded in a dark matter halo, then our motion through that halo creates a kind of relative wind or flow of dark matter particles passing through our local neighbourhood. Not wind in the sense of blowing curtains or tousling hair, much gentler than that. A particle wind, if you like, measurable only with sensitive instruments and theoretical patience. Imagine walking through mist so fine that no droplet touches your skin, yet countless droplets occupy the air around you. You would move through a medium without feeling it. Dark matter may be somewhat analogous, though made of whatever unknown particles nature chose rather than water. Scientists estimate a local dark matter density near the solar system from stellar motions and galactic modelling. Once a candidate particle mass is assumed, that density can be translated into a number of particles crossing a given area per second. Under many scenarios, the resulting flux is immense. Your body, your room, your city, the whole Earth may be immersed in a silent stream. That sounds extraordinary because human intuition links abundance with noticeability. If many things pass through me, surely I should know. But abundance and detectability are different questions. There are countless radio waves passing through your room right now if modern life is functioning normally, and perhaps even if it is not. Signals from routers, phones, towers, satellites and devices fill the space. You do not feel them as a swarm. There are enormous numbers of air molecules striking surfaces constantly, yet you only notice when organised movement becomes wind. There are photons from distant stars crossing your body nightly, without introducing themselves individually. Large numbers alone do not guarantee sensation. What matters is interaction. Dark matter appears to interact so weakly that even immense flux may remain effectively silent. This is one reason direct detection experiments are both difficult and fascinating. If many particles are passing through Earth continuously, perhaps one now and then will scatter off an atomic nucleus inside a detector. Such an event could create a tiny flash, charge signal, phonon vibration, or other measurable trace, but the signals are expected to be rare and delicate, hence detectors made from ultra-pure materials, hence cryogenic systems, hence underground laboratories shielded from cosmic rays and ordinary background radiation, hence years of patient data collection in pursuit of a few possible whispers. Humanity can be wonderfully stubborn when curious. Now let us imagine the room where you are listening. Perhaps there is a lamp, a ceiling, a wall, a window, some books, clothes draped over a chair with more optimism than order, and the pleasant stillness of a late hour. Everything seems settled, yet beneath that stillness physics is busy. Atoms vibrate thermally, air molecules collide chaotically, Earth rotates, the planet moves around the sun, the solar system orbits the galaxy, neutrinos from the sun pass through you, photons from distant sources continue their journeys, and perhaps dark matter particles stream through the scene as well. Stillness, it turns out, is often only a human scale impression. At deeper scales, motion never quite clocks out. There is something soothing in this once you make peace with it. Quiet does not require emptiness. Rest does not require universal stillness. A sleeping forest contains insects, roots, winds, microbial life, moonlit tides, and moving stars overhead. Likewise, a restful room may exist inside a very active cosmos. Another question often arises here: if dark matter particles are so numerous in some models, could they accumulate inside Earth or inside us? In most standard scenarios, not much. Because interactions are so weak, particles mostly pass through rather than getting trapped efficiently. Some gravitational capture by large bodies may occur under certain conditions, and scientists study such possibilities, but not in a way that turns people into storage containers for exotic matter. You remain composed chiefly of ordinary atoms and evening decisions. Dark matter does not secretly replace your lunch. There is also a seasonal twist that researchers consider. Because the Earth orbits the Sun while the solar system moves through the galaxy, the relative speed of Earth through the dark matter halo changes slightly over the year. This could create a small annual modulation in detection rates. Some experiments have searched for such patterns. The idea is charmingly subtle. Not weather seasons, but particle seasons. Spring, summer, autumn, winter, and perhaps a slight variation in hypothetical galactic flux. Reality often contains more layers than expected. Now let us talk scale again, because scale rescues many confusing facts. Suppose I tell you trillions of microscopic particles pass through an area constantly. That sounds enormous. Yet if each particle barely interacts and carries tiny relevant effect, the practical result may still be negligible. A beach can contain countless grains of sand while one grain against your shoe matters little. A cloud can hold vast droplets while a few on skin are barely noticed. Likewise, huge particle counts do not imply huge experience. The same principle applies elsewhere in science. The sun emits unimaginable numbers of photons, yet moonlight can still feel gentle, because what reaches you at night is sparse and indirect. Large totals somewhere do not automatically become dramatic effects here. Dark matter teaches this repeatedly. enormous cosmic importance, tiny local noticeability. There is something elegant about a universe where significance does not always announce itself loudly. We often assume power must be obvious, yet gravity is invisible, genes are microscopic, air is transparent, time itself cannot be touched, and dark matter, if real as modelled, may shape galaxies while passing through bedrooms unnoticed. Subtlety can scale. One philosophical comfort in all this is that hidden motion need not be threatening. Many people hear particles passing through you and instinctively tense because invisible activity sounds suspicious. But invisible activity is normal. Your own body is a city of cells exchanging signals. Molecules move constantly. Proteins fold and unfold. Blood circulates. Neurons fire. You're already an ecosystem of unseen processes. The cosmos simply extends the pattern. Life is not a static statue placed inside reality. It is a dynamic process nested inside larger dynamic processes. Tonight, while you rest, your heart works, cells repair, the Earth turns, the galaxy rotates, and perhaps dark matter continues its quiet transit through all of it. No disturbance required. This also explains why science communication must be careful with language. If one says, billions of particles are passing through you right now, it can sound alarming or sensational. A better phrasing would be, depending on the nature of dark matter, our region of space may host a substantial flux of weakly interacting particles that traverse ordinary matter with negligible everyday effect. Less dramatic, perhaps. Also less likely to startle someone trying to fall asleep. Still, wonder survives precision. Because even in the calmest phrasing, the idea remains remarkable. We may live immersed in a hidden particle environment tied to the structure of our galaxy, with streams crossing us moment by moment while senses remain entirely unaware. The room seems still. The universe is not. If so much may be moving through us, why is it so silent? Why no glow, no friction, no collisions lighting up space? By now we have followed dark matter from spinning galaxies to cosmic inventories, from invisible halos to the possibility of countless particles quietly moving through the room around you. And if all of that is true, one feature stands out above the rest. It's silence. Not silence in the poetic sense. Not the hush of snowfall or the pause after midnight when even the refrigerator seems to reflect on life. A physical silence. Dark matter does not appear to glow. It does not scatter light into our eyes. It does not crash into ordinary matter in obvious ways. It does not light the sky with trails or make walls hum as it passes through them. It is present, if our models are right, yet almost completely quiet to the senses and to many of our instruments. That is why it remained hidden so long, and that is why finding it is so difficult. We are used to learning about the universe through signals. In fact, nearly all classical astronomy began as signal reading. Stars shine, nebulae glow, planets reflect sunlight, hot gas emits X-rays, cold dust radiates in infrared, atoms absorb specific wavelengths, galaxies produce radio waves. Even black holes, despite the name, reveal themselves through surrounding matter-heating jets, accretion disks, and gravitational effects. The cosmos is usually talkative. Dark matter appears reserved. Imagine trying to study a city at night by looking for lights in windows. You could map neighbourhoods, streets, towers, and movement patterns. But suppose a vast district existed where nothing emitted light at all. No lamps, no signs, no headlights, no glowing windows. Yet roads bent around it, traffic patterns changed near it, and nearby buildings leaned under its weight. You would know something substantial was there, but it would be frustratingly quiet. That is the dark matter problem in spirit. Now, to understand why it is silent, we return to forces. Ordinary matter interacts through several fundamental forces, but for everyday visibility one force matters enormously. Electromagnetism. Electromagnetism governs light. Electricity, magnetism, chemistry, atomic bonds, and the behaviour of charged particles. Because ordinary matter contains charged constituents such as electrons and protons, it interacts richly with electromagnetic radiation. This is why things can shine, reflect, absorb, heat, burn, sparkle, glow, cast shadows, and generally participate in visual drama. A spoon can gleam, a candle can flicker, a star can blaze, a phone screen can demand attention at exactly the wrong hour, all electromagnetic behaviour. Dark matter seems not to do much of this. If dark matter particles carry no electric charge and interact little or not at all with photons, then light passes by without meaningful conversation, no reflection, no absorption in familiar ways, no emission from heating, no visible surfaces, no glowing clouds, no twinkling dark matter constellations. That is the first layer of silence. It does not speak light. There is a second layer. Ordinary matter also collides efficiently with itself and with other ordinary matter. Gas clouds crash, compress, heat, cool, and radiate. Dust grains stick, molecules bounce, rocks collide with discouraging confidence. Dark matter seems far less sociable. If its self-interactions are weak or rare, then dark matter particles may pass through one another and through ordinary matter with minimal friction. They do not easily lose energy by collisions the way gas does. This helps explain why dark matter forms broad halos rather than cooling into bright rotating disks of stars and planets. Ordinary matter can shed energy and settle. Dark matter appears to drift and cluster differently. No sparks, no smoke, no cosmic traffic jam with honking, just gravitational gathering on large scales. That quietness makes detection difficult because many scientific instruments rely on deposited energy. A particle enters, it collides. A flash occurs, charge is produced, heat changes slightly, something measurable happens. If interactions are extremely rare, detectors must wait patiently for tiny signals against constant background noise, and background noise is abundant. Natural radioactivity from rocks, cosmic rays from space, thermal fluctuations, electronic interference, trace contaminants. Even materials that look pure may contain minute radioactive impurities capable of mimicking sought-after signals. So researchers go underground, build shielded detectors, purify materials obsessively, cool systems, calibrate responses, and analyze data with care. All to hear something that may barely whisper. There is something admirable about this form of listening. Humanity looked at the universe, realized most of its matter may be invisible, and responded by constructing exquisitely sensitive ears and caverns. We are a determined species when puzzled. Now, let us consider the room around you again. Suppose dark matter truly passes through the walls, the floor, the air, your clothing, your body, and onward through the earth. Why no friction? Why no warmth? Why no tiny breeze? Because friction, warmth, and drag require repeated interactions that transfer momentum and energy. Air resists motion because molecules collide with surfaces constantly. Water pushes harder because it is denser and interacts strongly. A blanket warms because fibers trap air and reduce heat flow. Dark matter appears not to engage in such ordinary exchanges. You move through a dark matter environment, if one surrounds us, much as light moves through clear glass better than through stone. Little conversation, little resistance. This may feel strange because we often equate presence with impact. If something is there, surely it should matter locally. Yet nature offers many counterexamples. Neutrinos pass through Earth mostly unnoticed. Radio waves cross cities silently. Magnetic fields thread space invisibly. The vast majority of atoms are empty structured space rather than tiny packed solids. Reality often contains presence without drama. Dark matter may be one of the finest examples. Another reason silence matters is psychological. Humans trust vivid things. We trust bangs, flashes, heat, movement, scent, immediate consequence. A quiet influence feels less real than a loud one. But many powerful phenomena are subtle. Gravity never shouts. Time never bangs on the door. Evolution proceeds without fanfare. Continental plates move in patient millimeters until mountains exist. Likewise, dark matter may shape galaxies while refusing spectacle. There is a lesson in that. Importance and noise are unrelated. The night sky itself teaches this. Stars seem dominant because they shine, yet empty-looking space between them contains fields, particles, radiation, dust, and structure. What appears blank is often busy. Dark matter extends that lesson further. What appears empty may be occupied. What appears silent may be influential. What appears absent may simply be hard to hear. Now, there is an interesting scientific nuance here. Silence does not necessarily mean zero interaction. Dark matter may have weak interactions beyond gravity that are simply tiny or rare. Many theories predict exactly that. Some candidates might scatter occasionally off nuclei. Others might convert under special conditions. Some may self-interact modestly. Researchers test these possibilities continuously. So when we say silent, we mean silent compared with ordinary matter, not absolutely mute in every conceivable experiment. A whisper is still sound. We just need the right room to hear it. That is why some detectors use noble liquids like xenon or argon. Others use crystals, superconducting sensors, resonant cavities, or astrophysical observations. Different methods listen for different kinds of whispers. Some seek tiny recoils. Some seek photon conversions. Some seek annihilation products in space. Some seek deviations in stellar behavior or structure formation. Human curiosity, when blocked at one door, tends to try the windows. There is also a beautiful irony in all this. Dark matter may be the dominant matter component of the universe, yet it is the least showy. Meanwhile, ordinary matter, a smaller share, creates stars, sunsets, coral reefs, violins, bread crust, thunderstorms, and candlelight. The minority ingredient handles aesthetics. The majority may handle scaffolding. The universe, once again, declines to match social expectations. You might wonder whether one day this silence will end. Perhaps. If a direct detection experiment captures a convincing signal, if a collider produces candidate particles, if astrophysical evidence narrows the possibilities sharply, if new theory reframes the whole question, then dark matter would move from inferred presence to identified participant. Still quiet perhaps, but finally named properly. Until then, we live in an interesting era. One where we know something vast is likely there, yet not exactly what it is. That position can feel frustrating if you crave final answers. It can also feel thrilling if you appreciate living near the frontier of knowledge. Not every generation gets handed a mystery this large, and while dark matter remains silent to our eyes and ears, it has not been completely mute. After spending time with the silence of dark matter, we come to a question that sits at the centre of the whole mystery. If we cannot see it directly, how do we know it is there at all? It is a fair question, and one worth answering carefully, because science is not built on dramatic guesses or mysterious labels handed out for effect. It is built on evidence, consistency, prediction, measurement, and the patient comparison between what should happen and what actually does happen. Dark matter entered science not because someone wanted the universe to be spooky, but because the universe kept behaving as though unseen mass were present. That distinction matters. Scientists are not claiming to have opened a cosmic cupboard and found jars labelled dark matter. They are saying that many independent observations make more sense if some additional invisible mass exists. We know it indirectly, and indirect knowledge, though sometimes less emotionally satisfying than pointing at a glowing object, is one of the most powerful tools in science. You already use indirect reasoning constantly. You wake and see wet streets. It likely rained. You hear footsteps upstairs. Someone is moving. You smell toast. Either breakfast is happening or a small emergency has begun. You do not need to witness every cause directly. Effects often speak clearly enough. Astronomy works the same way, except with better mathematics and fewer burned appliances. Let us begin with motion. One of the earliest and strongest clues came from galaxies themselves. As we discussed earlier, stars far from galactic centres move faster than visible matter alone predicts. If only the glowing stars, gas and dust supplied gravity, many outer stars should drift away or orbit more slowly. Yet they do not. They remain bound and move rapidly. That tells astronomers more mass exists than telescopes see in visible light. Imagine watching children spin a ball on a string. If the string were too weak, the ball would fly off. If it stays in a fast circle, the inward pull must be strong enough. Likewise, fast orbiting stars imply sufficient gravitational pull. When the visible matter cannot provide it, unseen mass becomes a leading explanation. This evidence appears across many galaxies, not just one odd example having an adventurous evening. Repeated patterns strengthens confidence. Now let us move to galaxy clusters, even larger structures containing hundreds or thousands of galaxies. Within these clusters, galaxies move around one another at speeds revealing how much total gravity is present. Measurements show that visible matter alone does not provide enough mass to hold clusters together. Again, too much motion for too little visible weight. Then X-ray observations revealed hot gas-filling clusters. This gas contributes substantial ordinary matter, which was an important discovery. Yet even after counting it, there was still missing mass. The suitcase remained heavy, so now we had unseen mass implied by individual galaxies and by giant clusters. That would already be significant. But then gravity offered an even more elegant demonstration. According to Albert Einstein's general relativity, mass curves space-time. Like travelling through curved space-time changes path. In practical terms, massive objects can bend light from more distant sources behind them. This effect is called gravitational lensing. A galaxy or cluster can act like a lens, distorting the images of background galaxies. Sometimes the effect is subtle, slightly stretching shapes. Sometimes it is dramatic, producing arcs, rings, or multiple images. By measuring these distortions, astronomers can estimate how much total mass lies in the foreground object. Here is the key point. The lensing often indicates more mass than visible matter supplies, and lensing does not care whether mass glows. Gravity bends light regardless of whether the mass is a star, gas cloud, black hole, or something unseen. So gravitational lensing allows scientists to map invisible mass directly through its gravitational effect. It is one of the most beautiful methods in astronomy, seeing the unseen by how it redirects the light of things behind it. Imagine walking across fresh snow and noticing curved tracks leading around an object hidden under a blanket. You cannot see the object itself, but the paths reveal its presence. Lensing works similarly. The background light is the path. The hidden mass shapes the route. One especially famous example is the Bullet Cluster. Two galaxy clusters collided. Their hot gas, which is ordinary matter, interacted strongly and slowed. The galaxies mostly passed through. When astronomers mapped visible gas using X-rays, it sat in one place. When they mapped mass using lensing, much of the mass appeared offset, travelling with the galaxies rather than the gas. This suggested a large component of matter that did not behave like collisional ordinary gas. Something unseen seemed to have moved through. The Bullet Cluster became a powerful case because it visually separated where the visible matter was from where much of the gravitational mass was. Now, let us step further outward, to the early universe. The cosmic microwave background is faint radiation left over from when the universe was young, hot, and dense. Tiny temperature fluctuations in this ancient light encode information about matter content, geometry, and cosmic evolution. When missions such as NASA's WMAP and European Space Agency's Planck spacecraft measured these patterns precisely, the best fit cosmological models again indicated more matter than ordinary atoms alone provide. different era of the universe, different data source, same conclusion. Then there is cosmic structure itself. Galaxies are not sprinkled randomly like confetti. They form filaments, clusters, sheets, and vast webs across space. Simulations show that structure grows in ways consistent with invisible matter, helping seed gravitational wells early on. Without dark matter or some equivalent modification, reproducing today's large-scale structure becomes much harder. So now we have evidence from galaxy rotation, cluster dynamics, hot gas accounting, gravitational lensing, ancient background radiation, large-scale structure formation, different methods, different times, different scales, converging result. This convergence is crucial. Science becomes stronger when many independent lines of evidence point to the same answer. If one measurement alone suggested missing mass, skepticism would be healthy. If 6 unrelated methods do so, confidence rises substantially. Think of it this way. Suppose one friend tells you a bakery in town is excellent, interesting. Then another praises the bread, another praises the pastries, a neighbour praises the coffee, reviews mention long lines, you smell fresh baking while passing outside. At some point the evidence converges and you reasonably conclude the bakery is real and probably worth visiting. Dark matter's case is more mathematically serious, of course, but the logic of convergence is similar. Now, an important nuance. Some scientists explore alternatives to dark matter, particularly modified gravity theories. These propose that gravity behaves differently on certain scales, reducing or replacing the need for unseen matter in some contexts. This is a legitimate scientific avenue. However, explaining all the evidence simultaneously has proven challenging. Some modified gravity ideas address galaxy rotation curves elegantly, but struggle elsewhere, while dark matter models naturally fit several large-scale observations. The debate sharpens understanding either way. Science benefits from competing explanations forced to face data. Another question people ask is whether dark matter could simply be ordinary objects too dim to see. Faint stars, rogue planets, cold gas, black holes. Some hidden ordinary matter exists, certainly. But precise cosmological measurements limit how much ordinary baryonic matter the universe contains. There is not enough to explain the full discrepancy. So while dark corners contain real things, they do not solve the whole puzzle. There is also something philosophically lovely about this method of knowing. Humans often imagine knowledge as direct sight. If I see it, I know it. Yet much of our deepest understanding comes indirectly. We infer atoms from experiments. We infer interiors of stars from spectra and physics. We infer black holes from surrounding motion and radiation. We infer tectonic plates from earthquakes, coastlines, and geology. We infer dark matter from gravity's bookkeeping. Direct vision is wonderful, but not the only path to truth. Indeed, sometimes indirect methods reveal things direct senses never could. You cannot see radio waves, but antennas do. You cannot feel bacterial colonies unaided, but microscopes reveal them. You cannot watch space-time curve with naked eyes, but lensing maps can show it statistically. Human knowledge grows by building better senses. Telescopes extended sight, spectroscopy extended colour, detectors extended touch into particle realms, mathematics extended pattern recognition beyond instinct. Dark matter sits at the frontier of all four. Now, let us bring this gently back to the room where you are listening. You may not see dark matter around you. You may never directly sense it. Yet the evidence for its existence does not depend on your room. It comes from galaxies, clusters, background radiation, and the architecture of the cosmos itself. The case was built far from the bedside, but if correct, it includes the bedside too. That is often how cosmic truths work. They are discovered on large scales and then quietly apply everywhere. Gravity was inferred and formalized through falling apples, moons, and planets alike. Dark matter, if real as modelled, is inferred through galaxies and clusters, yet likely extends through our local galactic neighbourhood. So when scientists say they know something unseen is there, they do not mean certainty without evidence. They mean evidence so broad and repeated that ignoring it would be harder than accepting it. Once scientists became convinced that galaxies contain far more mass than their stars, gas and dust could explain, another question naturally followed. Where is that mass arranged? If dark matter exists, does it sit neatly in the bright spiral arms? Does it gather in clumps like clouds? Does it hide near the centre in one dense lump? Does it spread thinly through all of space like a uniform mist? The answer suggested by observations and simulations is both elegant and surprising. Galaxies appear to live inside enormous structures called dark matter halos. A halo, in this context, is not a glowing ring hovering above a galaxy like celestial approval. It is a vast region of dark matter, surrounding and extending far beyond the visible parts of the galaxy. Roughly speaking, the shining galaxy you see may occupy only the bright inner portion of a much larger invisible mass distribution. That idea changed how astronomers picture galaxies. A galaxy is not merely a disk of stars turning in empty space. It is more like a luminous settlement built inside a much larger gravitational landscape. Take our own Milky Way. What we notice in photographs is the familiar disk. Spiral arms, stars, gas lanes, clusters, and the bright central bulge. Yet current models suggest the Milky Way is embedded in a dark matter halo extending far beyond the visible disk. The stars are the lanterns. The halo is much of the hidden terrain. Now, how did scientists arrive at this picture? Let us return to rotation curves. Outer stars in spiral galaxies move faster than expected if only visible matter supplied gravity. One way to explain that is additional mass distributed well beyond the bright stellar disk. If the unseen mass were concentrated only at the centre, the speeds would fall differently. If it were confined to spiral arms, patterns would differ again. Instead, many galaxies behave as though they are immersed in extended envelopes of mass, hence halos. Imagine a town at night viewed from a hill. Streetlights mark roads and buildings. You might think the town ends where the lights end. But if you could somehow feel the pull of buried foundations, water systems, roads, and surrounding terrain, you might discover the functional footprint extends much farther than illumination suggests. Galaxies may be like that. The visible lights mark where ordinary matter became stars. The gravitational footprint stretches much farther. Halos are not thought to be rigid shells. They are dynamic particle distributions. If dark matter consists of particles, then a halo would be more like an enormous swarm or cloud, bound by gravity than a solid structure with edges you could knock on politely. No wall, no roof. No dramatic boundary line reading halo begins here. Instead, density tends to be greatest nearer the centre and gradually decreases outward, though the exact profile depends on models, mergers, history and ongoing research. That means if you moved outward from a galaxy's bright disk, you would not cross a sharp border from matter to no matter. You would pass through thinning regions of invisible mass. Nature often prefers gradients to neat lines. Coastlines blur into sea. Atmosphere fades into space. Forests thin into grassland. Dark matter halos likely soften outward rather than stopping abruptly. Now, why are halos important? Because they may be the gravitational frameworks within which galaxies formed. In the early universe, ordinary matter was strongly coupled to radiation for a time. Dark matter, interacting weakly, could begin clumping earlier under gravity. Those clumps became seeds, wells into which ordinary matter later fell, cooled, and formed stars. If so, halos came first in a structural sense. The galaxy's visible components assembled inside pre-existing dark matter potential wells. That is a profound shift in perspective. We often imagine stars as the main event and everything else secondary. but galaxies may have formed because invisible scaffolding existed first. It is a bit like admiring a cathedral while forgetting the foundations beneath it. The visible inspires awe. The hidden made it possible. Simulations of cosmic structure formation support this picture. When cosmologists model universes containing dark matter, large-scale structures resembling observed galaxy networks emerge more naturally. Halos form, merge, grow, and host galaxies. Small halos may host dwarf galaxies. Large halos host spiral galaxies. Enormous halos host galaxy clusters. In this sense, halos are like cosmic addresses where ordinary matter sets up residence. There is something wonderfully practical about the universe if this is true. Before stars made scenery, gravity prepared real estate. Now let us talk shape. The word halo sometimes suggests perfect spheres, but reality may be messier. Halos are often approximated as roughly spherical or ellipsoidal, especially compared with the flat rotating disks of spiral galaxies. Yet simulations indicate triaxial shapes, substructure, distortions from mergers, and evolution over time. Translation into calmer language. They are likely not perfect beach balls. They are shaped by history. When galaxies merge, halos interact gravitationally. When satellites fall in, streams and clumps can remain. When matter accretes unevenly, shapes respond. The invisible carries memory through structure. That should sound familiar. Visible galaxies also bear scars of collisions, bars, warp disks, tidal streams, and asymmetries. The unseen component likely shares in this long biography. Another fascinating feature is subhalos. Within larger halos, smaller concentrations of dark matter may survive, orbiting inside them. These subhalos are thought to host many dwarf galaxies and satellite systems. Our own Milky Way has satellite galaxies such as the Large Magellanic Cloud and Small Magellanic Cloud, along with many dwarf companions. These likely inhabit substructures within the larger halo environment. So halos are not empty, smooth blobs. They may contain hierarchy, structure within structure, neighborhoods within cities within nations, in a loose sense. This nesting behavior is common in nature. Rivers have tributaries, trees have branches upon branches, weather contains storms within fronts within planetary circulation. The universe often builds complexity by layering scales. Dark matter halos may be another example. Now let us bring this back to you. Where is the solar system inside the Milky Way halo? We orbit within the galaxy's disk, well away from the central bulge, embedded in the broader halo region. That means our local environment is not outside the dark matter structure but inside it. We are residents, not visitors. You're listening tonight from somewhere within a giant invisible galactic envelope, extending far beyond the stars most people imagine as the galaxy's limit. The Milky Way's visible disk is already enormous. The halo likely extends much farther still. This can be mentally refreshing. Human worries often shrink appropriately when placed inside a structure so large that even our galaxy's bright part is only the inner feature of something larger. Deadlines remain real, of course, but perspective gains room. Another question arises naturally. If halos are everywhere around galaxies, why don't we see them through light from their own particles? Because dark matter appears not to interact electromagnetically in familiar ways. No glow, no reflection, no ordinary absorption. The halo announces itself mainly through gravity, star motions, satellite orbits, lensing effects, and structure formation. Again, the invisible leaves footprints rather than portraits. There is a lovely irony here. Halos may determine much of a galaxy's mass, yet most astronomy images show only the smaller luminous part. It is as if every family portrait captured clothing and smiles while omitting the entire skeleton. Useful image, incomplete inventory, modern astronomy tries to supply the missing anatomy. How do scientists estimate halo masses? Several methods combine: rotation curves of spiral galaxies, motions of stars in elliptical galaxies, satellite galaxy orbits, hot gas temperatures in larger systems, gravitational lensing, cosmological simulations matched to observations. No single method is perfect. Together they build a consistent picture. This is often how science handles the unseen, multiple partial windows instead of one magical reveal. Now, are halos truly made of particles, or could modified gravity mimic them? This remains an active area of inquiry. Modified gravity theories attempt to explain some observations without particle dark matter, yet the halo framework fits many datasets and remains central in mainstream cosmology. Even if future theory revises details, the current halo concept is extraordinarily useful. It organises observations elegantly. An elegant usefulness often survives into deeper truth, even if names or mechanisms later change. Think of early atomic models. Not fully correct, still profoundly useful stepping stones. Halos may occupy a similar role, or may prove substantially accurate in detail. Ongoing evidence will decide. There is also something emotionally satisfying about halos compared with abstract missing mass. Missing mass sounds like lost paperwork. Halo gives shape, place, architecture. Humans like turning mysteries into maps. We want to know not only that something exists, but how it is arranged. Once astronomers began to understand that galaxies likely live inside dark matter halos, another realization slowly came into focus. Those halos are not isolated islands. Galaxies are not scattered randomly through space like confetti tossed by an enthusiastic but disorganized universe. They gather in groups, clusters, filaments, sheets, and long connected structures stretching across astonishing distances. The cosmos, on its larger scales, appears woven, and much of that woven architecture is thought to be guided by dark matter. This grand arrangement is often called the cosmic web. It is one of the most striking ideas in modern cosmology, that the universe is not just a collection of separate galaxies floating independently in emptiness, but a vast network of matter organized into strands and nodes, with immense voids between them. Imagine dewdrops clinging to a spiderweb at dawn. The drops catch your eye first because they shine. But the web is what gives them pattern. Galaxies may be like the dew. Dark matter, in part, may be much of the hidden web. Now, let us be careful with the metaphor. The cosmic web is not made of silk, threads you could pluck like strings. It is a large-scale structure formed by gravity acting over billions of years. Matter, especially dark matter, gathered into denser regions. Those regions linked into filaments. Where filaments intersected, clusters of galaxies formed. Between them lie enormous underdense expanses called cosmic voids. No weaving loom was involved, though one suspects the universe would have enjoyed the drama. How did scientists discover this structure? At first, astronomers mapped galaxies one by one. As surveys improved, especially in the late 20th century and beyond, patterns emerged. Galaxies were not uniformly sprinkled through space. They formed walls, chains, clusters, and bubbles around giant emptier regions. Projects such as the Sloan Digital Sky Survey and other large surveys helped reveal this in increasing detail. When plotted in 3 dimensions, the distribution of galaxies looked less like random dust and more like a living network. This was a major clue. Something had guided structure formation at enormous scales. Dark matter became central to that explanation. To understand why, we return briefly to the early universe. Soon after the Big Bang, matter was not arranged into galaxies. It was much smoother, though not perfectly smooth. Tiny density differences existed, slightly denser here, slightly thinner there. Over time, gravity amplified those differences. Denser regions pulled in more matter. More matter increased gravity. Increased gravity pulled in more matter still. Small unevenness became large structure. That process happened with ordinary matter, yes, but dark matter may have played a special early role. Because it did not strongly interact with radiation the way ordinary matter did, it could begin clumping earlier and more efficiently. In effect, dark matter may have formed the first major gravitational framework into which ordinary matter later fell. If so, galaxies did not simply appear from visible gas alone. They condensed inside pre-existing invisible valleys of gravity. That is a remarkable picture. The stars we admire may have formed inside structures built first by something we still cannot directly identify. The visible world, once again, may be the decoration atop hidden architecture. Now, what does the cosmic web actually look like? Imagine enormous filaments hundreds of millions of light years long. Along these strands sit galaxies and clusters like towns along highways. Where several filaments meet, giant clusters gather. Between strands lie voids so vast and sparse that if you lived there, the night sky could be dramatically poorer in nearby galaxies than what we see from our region. Even emptiness has geography. That sentence may be one of cosmology's quieter delights. Voids are not absolutely empty. They still contain matter, radiation, perhaps a few lonely galaxies, and the usual rights reserved to space-time. But compared with clusters and filaments, they are strikingly underdense. The universe has neighbourhoods, suburbs, downtown centres, and rural stretches on scales that make maps blush. Now, why think dark matter is involved specifically? Because simulations. When cosmologists model the universe using known physics and include dark matter, structures resembling the observed cosmic web naturally emerge over time. Filaments form, halos grow, clusters arise at intersections, galaxies populate dense regions. When models omit dark matter entirely, reproducing the observed richness and timing of structure becomes much harder. Again, this does not prove every detail permanently settled, but it strongly supports dark matter as a key ingredient. Nature appears to match the version where hidden mass helps organize the stage. There is something deeply satisfying when mathematics, computer simulation, and telescope surveys begin telling the same story. Different tools, same pattern. Another elegant line of evidence comes from gravitational lensing on large scales. Because mass bends light, astronomers can statistically map matter distributions, including unseen components, by studying how background galaxies are subtly distorted across the sky. This technique, weak lensing, helps reveal where mass lies even when light does not. It is rather like inferring hills and valleys by watching how rolling marbles subtly curve across a floor hidden under carpet. When these maps are compared with visible galaxy surveys, the relationship between luminous matter and broader mass structure becomes clearer. The glowing beads often trace deeper invisible strands. Now let us bring some scale to this. The Milky Way belongs to the local group, which includes Andromeda Galaxy and many smaller galaxies. The local group is part of a larger region called the Virgo supercluster, often now contextualized within the even larger Laniakea supercluster. Already we are nested in structures within structures, galaxy within group, group within larger flows within cosmic web. You're not merely in a room, on a street, in a city, on a planet. You're also in a galaxy, inside a group, within a vast gravitational network stretching across the observable universe. One can forgive the laundry for seeming less central under such circumstances. There is also a calming emotional lesson here. Many people feel isolated under the night sky, imagining themselves as tiny points in emptiness. But the cosmic web suggests connectedness rather than isolation. Everything large-scale belongs to patterns, flows, relationships, structure. Galaxies are linked by common history and gravity. Matter gathers through interaction. Even voids are defined by surrounding form. The universe is not random loneliness. It is organized spaciousness. That may be a healthier phrase. Of course, we must avoid overstating the metaphor. Galaxies and filaments are still separated by immense distances. One should not expect to stroll next door to another cluster after breakfast. The scales remain enormous, yet pattern exists. Now, one of the more delightful scientific facts is that this web was invisible for most of human history, not because it was hidden maliciously, but because seeing large-scale structure required data from millions of galaxies. No ancient observer lacked wisdom for missing it. They lacked surveys, computers, redshift catalogues, and a few satellites. Sometimes truth waits for tools. The same may be true of dark matter's exact identity today. We know the structure, we still seek the substance. There is another subtle point worth appreciating. The cosmic web is not static. Gravity continues shaping it. Galaxies merge, clusters accrete matter, filaments channel material inward, the universe expands, structures evolve. The cosmos is not a finished sculpture, it is ongoing construction. Very slow construction, admittedly. You may not wake tomorrow to discover your neighbourhood annexed by a neighbouring cluster, but over immense timescales, motion continues. This reminds us that stillness is often a timescale illusion. Mountains move if you wait long enough. Forests migrate across centuries. Galaxies dance across eons. The cosmic web itself lives in slow motion. Now, could this web exist without dark matter if gravity behaved differently? Some alternative models attempt to reproduce large-scale structure through modified gravity or related frameworks. These remain areas of real research. Yet standard cosmology with dark matter remains highly successful in matching a wide range of observations. As always, evidence will keep the final vote. Science is not allegiance to labels, it is loyalty to what survives testing. Still, at present, dark matter is deeply woven into our best explanation of the universe's large-scale architecture. That makes the phrase dark matter feel less like an obscure particle hunt and more like something structural and grand, not merely hidden bits. The framework of cosmic neighbourhoods, the reason galaxies gather where they do, the scaffolding behind luminous geography. And perhaps the most charming irony of all is this: human beings, tiny creatures on one planet around one star in one galaxy, have managed to infer the existence of a vast invisible web spanning billions of light years by studying faint light, tiny shifts, careful statistics, and patient thought. A species that misplaces keys regularly has also mapped the skeleton of the cosmos. Both facts can be true. For a mystery this large, honesty demands a certain humility. Dark matter is one of the strongest working ideas in modern cosmology, supported by multiple lines of evidence, useful in simulations, and deeply woven into our current picture of the universe. Yet there is an important distinction between saying, "This model explains many observations," and saying, "We know the final answer beyond doubt." Those are not the same statement. So tonight, we arrive at a wonderfully scientific question. Could dark matter be something entirely different from what we currently imagine? Could the missing mass problem arise not from undiscovered particles drifting through halos, but from a misunderstanding of gravity itself? Could several phenomena be bundled under one label that later turns out to contain multiple causes? Could the universe be asking a better question than the one we first wrote down? History suggests such caution is wise. Science often begins with a successful placeholder concept that later becomes deeper, stranger, or more precise. Ancient astronomers described planetary motions with epicycles that worked reasonably well for prediction before better models emerged. Early chemists spoke of heat in ways later replaced by thermodynamics and statistical mechanics. Atoms were once thought indivisible. They were not. Useful ideas can be stepping stones. Sometimes they are nearly right. Sometimes they are right in effect but incomplete in mechanism. Sometimes they are eventually retired with gratitude. Dark matter may yet prove to be a new particle species exactly as many physicists suspect. But it is also possible that the full story contains surprises. That possibility is not weakness in science. It is science functioning properly. Let us begin with the most famous alternative family of ideas, modified gravity. Instead of adding unseen matter to explain extra gravitational effects, some researchers ask whether gravity behaves differently on very large scales or at extremely low accelerations. If the law of gravity changes slightly in certain regimes, Perhaps galaxies rotate faster than expected without requiring invisible mass. One influential example is modified Newtonian dynamics, proposed by Mordechai Milgrom in the early 1980s. The core idea is surprisingly simple. Newton's laws work extremely well in many everyday and astronomical settings, but perhaps when accelerations become incredibly tiny, as in the outskirts of galaxies, the relationship changes. Under such conditions, stars might orbit faster than standard expectations predict. MOND gained attention because it can reproduce many galaxy rotation curves quite effectively, sometimes with striking elegance. That matters. Any fair discussion must acknowledge when a competing idea explains real data. Science is not team sports with jerseys and chants. It is comparison under evidence. If one framework predicts certain galactic behaviours neatly, it deserves attention. Yet MOND and related approaches face challenges elsewhere, especially when moving beyond individual galaxies to galaxy clusters, gravitational lensing, and cosmological observations such as the cosmic microwave background. Some relativistic extensions of modified gravity attempt to address these issues with frameworks like TeVe's and others. The debates are technical, ongoing, and worthy of careful study. At present, the mainstream cosmological model, including dark matter, remains more broadly successful across many datasets. Still, alternatives serve an essential role. They pressure test assumptions. They reveal where standard models truly shine and where they merely coast on habit. They keep science awake. There is something admirable about that. Now let us consider a second possibility. What if dark matter exists, but not as one single particle type? This is increasingly plausible as a conceptual space. We often speak of dark matter as though it were one thing, like saying water or iron. But the universe may prefer categories richer than singular labels. Ordinary matter itself is not one particle. It includes quarks, electrons, neutrinos, atoms, molecules, plasma, stars, planets, bacteria, bread crusts, and the occasional missing sock undergoing independent history. Why assume the dark sector must be simpler? Some theorists explore dark sectors, where dark matter could include multiple particle species, forces, interactions, or states hidden from ordinary electromagnetism. There could be dark analogues of complexity we have not yet imagined fully. Not dark people, dark furniture, or dark tax systems. Particle sectors. One must be careful with language. Such models remain speculative, but they remind us that the phrase dark matter may conceal a family resemblance rather than a single identity. Another possibility is that part of the missing mass story involves compact objects. Could large populations of black holes, faint remnants, or exotic dense bodies account for some dark matter? This idea has been explored in various forms, including renewed interest in primordial black holes formed early in cosmic history. Observations constrain many versions strongly. Too many black holes of certain masses would produce lensing events, mergers, or other signatures we should notice. Yet some parameter ranges remain studied. Again, uncertainty does not mean anything goes. It means evidence narrows options over time. Then there is a subtler possibility. What if our current separation between dark matter and dark energy is incomplete? Could both arise from a deeper common framework we do not yet understand? Might gravity, space-time, quantum fields, and cosmic expansion be parts of a larger theory from which these phenomena emerge differently than we currently label them? Many researchers pursue ideas along these lines, though none has yet replaced the standard picture convincingly. Still, major breakthroughs often begin where categories start to blur. Electricity and magnetism were once separate phenomena before unification into electromagnetism. Space and time were once conceptually distinct until relativity fused them into space-time. Perhaps future theory will unify mysteries we currently list separately, or perhaps not. The universe has no duty to simplify itself for our convenience. There is also the possibility that dark matter is mostly correct. but our simulations of galaxy formation need refinement in how ordinary matter behaves. Feedback from supernovae, black holes, gas dynamics, star formation, turbulence, magnetic fields, and environmental history can significantly affect visible structures. In simpler terms, galaxies are messy, very messy. Any model trying to compare theory with real galaxies must account not only for invisible matter, but for exploding stars, heating gas, cooling gas, mergers, chemical enrichment, jets from black holes, and billions of years of accumulated complications. So sometimes tensions between prediction and observation may reflect astrophysical complexity rather than failure of dark matter itself. This is common in science. When a recipe disappoints, the problem may be the ingredients, the oven, the timing, the measurements, or the cook reading only half the instructions. One should diagnose carefully. Now let us ask a philosophical question hiding underneath all this. Why do people sometimes resist dark matter as an idea? Partly because it is invisible, partly because it sounds like adding an unseen ingredient to rescue equations, and partly because humans prefer explanations that feel direct and intuitive. If something moves strangely, perhaps the law changes rather than hidden stuff appearing. That instinct is understandable, but nature has repeatedly shown that unseen entities can be real and fruitful explanations. Atoms were unseen long before imaging techniques. Microbes were unseen before microscopes. Neutrinos were inferred before direct detection. Planets beyond our solar system were predicted before many were observed. Indirect evidence is not second-class evidence when robustly gathered. At the same time, skepticism has value. Demanding stronger proof led to better experiments, sharper models, and more rigorous cosmology. Both trust and doubt have roles when disciplined. Too much trust accepts flimsy stories. Too much doubt rejects real clues. Science tries to steer between those cliffs. There is something calming in that balance. We do not need perfect certainty tonight. We need honest progress. And honest progress says this: dark matter is currently the leading explanation for a wide range of cosmic observations. Its exact identity remains unknown. Alternative theories exist and continue to be tested. Future discoveries may confirm current expectations, refine them, or surprise us substantially. That is a healthy place to stand. Not confusion, not dogma, open confidence. You might compare it to hearing footsteps in another room. You know someone is there from repeated evidence. Whether it is one person, two people, or the cat having ambitious ideas remains to be determined. Now, if dark matter were something entirely different, what would happen? Physics would become very exciting very quickly. Textbooks would be revised, simulations rerun. Researchers would lose sleep voluntarily. Many careers would become unexpectedly interesting. The public would briefly discover affection for astrophysics. Then, as always, the new explanation would settle into normal knowledge, and children in future classrooms would ask why anyone ever found it mysterious. That is the rhythm of discovery. Today's frontier becomes tomorrow's paragraph. Still, we're not there yet. At present, detectors continue searching. Telescopes continue mapping. Theorists continue proposing. Data continues judging. Beneath mountains, inside old mines, under layers of rock that have watched centuries pass without comment, some of the most delicate scientific instruments ever built are waiting in the dark. They are not waiting for earthquakes. They are not searching for buried treasure. They are listening for dark matter. There is something wonderfully fitting about that. To investigate matter that does not shine, humanity often goes to places where sunlight never arrives. And yet the search does not stop underground. It also reaches into orbit, across deserts, beneath Antarctic ice, through radio dishes, particle colliders, satellites, and telescopes aimed into deep space. We are looking above and below, inward and outward, using nearly every method cleverness can afford. Because once scientists became convinced that unseen mass likely shapes the universe, The next obvious question was no longer, does something strange exist? It became, can we catch it? Now, let us begin below the surface. Why build dark matter detectors underground? The answer is noise. Earth's surface is constantly showered by cosmic rays, energetic particles arriving from space. Natural radioactivity also exists in rocks, air, building materials, and even in the human body. Electronic systems generate interference. Thermal motion creates background signals. If you are searching for an extraordinarily rare, tiny event, all this ordinary activity becomes a problem. Imagine trying to hear a whisper in the middle of a busy train station. Better to step into a quiet cellar. That is why researchers place detectors deep underground, where layers of rock block many cosmic rays and create a calmer environment for measurement. Famous underground laboratories include Gran Sasso National Laboratory beneath an Italian mountain, Snow Lab deep inside a mine, and Sanford Underground Research Facility in a former gold mine. There is something charmingly human about taking old tunnels once used to pull treasure from Earth and turning them into places that search for cosmic truth instead. Now, what sits inside these laboratories? Often, giant tanks or chambers filled with ultra-pure materials such as liquid xenon or liquid argon. Why xenon or argon? Because these noble elements are chemically stable, can be purified extremely well, and can produce detectable flashes or electrical signals if struck by a particle. The hope is simple. A dark matter particle passes through the detector. On an exceedingly rare occasion, it bumps an atomic nucleus. That tiny recoil creates light, charge, heat, or some combination. Instruments record it. Researchers then spend large amounts of time asking whether it was really dark matter, or merely something ordinary pretending to be interesting. This second step is essential. Science is full of signals that initially look exciting and later turn out to be background noise, contamination, calibration quirks, misunderstood statistics, or the scientific equivalent of mistaking a coat on a chair for a person at 2 a.m. Caution is not pessimism. It is quality control. Some of the best-known experiments in this category include Lux Zeppelin, often shortened to LZ, Xenon End-T, and Pandax. These detectors are astonishing feats of engineering. Ultra-pure liquids, sensitive photodetectors, shielding systems, careful temperature control, statistical rigor, all arranged to notice something that may almost never happen. It is a modern form of patience. Now let us widen the search. Not every strategy waits for particles to hit a detector directly. Some scientists look for dark matter indirectly by studying what might happen when dark matter particles annihilate or decay. If certain particle candidates collide with one another or slowly transform, they might produce gamma rays, neutrinos, positrons, or other detectable particles. So researchers watch the sky. They study regions where dark matter should be dense, such as the centre of the Milky Way, dwarf galaxies orbiting it, or galaxy clusters. Instruments like the Fermi Gamma Ray Space Telescope search for unusual gamma ray signatures. Other observatories monitor cosmic rays and neutrinos. This approach is like searching for smoke rather than the fire itself. You may not see the hidden fuel, but perhaps you catch its byproducts. Then there are particle colliders. At places such as CERN, home of the Large Hadron Collider, physicists smash particles together at immense energies. The hope is that such collisions might produce new particles, perhaps even dark matter candidates. Now, if dark matter were created in a collider, it would likely escape the detector without interacting much. That sounds inconvenient. Fortunately, physicists are experienced with inconvenient particles. They infer missing particles through missing momentum and energy balance. If known particles fly out one way while something unseen carries momentum another way, the event may hint at new physics. Again, we meet the recurring theme of this whole story. The unseen reveals itself by what everything else does. There is a pleasing consistency to that. Some searches focus on extremely light candidates such as axions. These require different tools, including resonant cavities, magnetic fields, and exquisitely sensitive microwave detection systems. Experiments like ADMX listen for faint conversions of axions into photons under strong magnetic conditions. This means somewhere in the world there are scientists trying to hear hypothetical particles become microwaves in carefully tuned chambers. Human curiosity is magnificently specific. Then there are searches using astronomy itself. Could dark matter subtly influence star motions, gravitational lensing patterns, galaxy formation histories, pulsar timing, or other measurable cosmic phenomena? Yes, and many teams pursue exactly that. The universe becomes both the mystery and the instrument. Even the cosmic microwave background helps constrain dark matter models by preserving clues about how matter behaved in the young cosmos. Ancient light is still contributing to present investigations. Now, an honest question deserves an honest answer. Have we found dark matter yet? Not definitively. There have been intriguing signals, debated anomalies, tentative hints, excesses in data, annual modulation claims, and many headlines eager for excitement. But no result has yet achieved broad scientific consensus as a confirmed direct discovery of dark matter's particle identity. That may sound disappointing. I would frame it differently. It means the universe is still interesting. If the first simple detector had found the answer immediately, we would have solved one mystery, but lost years of inventive searching, technical progress, and intellectual exploration. Sometimes difficulty is productive. Many technologies improve because of hard scientific problems. Low background materials, advanced sensors, data analysis methods, cryogenic systems, imaging tools, and statistical techniques often benefit broader fields. Even unanswered questions can generate useful tools. Another concern people sometimes have is whether these experiments are dangerous. For standard dark matter searches, no. These are controlled scientific facilities using known safety protocols. Underground detectors mostly wait quietly. Telescopes observe. Colliders operate under heavily studied physical principles. No portal openings are scheduled. No galactic leaks are expected. Your evening remains secure. There is also something moving about the scale of this effort. Thousands of people across countries, languages, institutions, and decades cooperate to understand matter no one has directly held. Engineers build instruments. Theorists propose models. Analysts sift data. Technicians maintain systems. Graduate students lose sleep for noble reasons, all because some galaxies spun too fast. That is how curiosity grows. One discrepancy becomes an international endeavour, and even failure in such searches is informative. If detectors see nothing in a certain range, that rules out possibilities. If colliders fail to produce candidates at certain energies, models narrow. If telescopes do not find expected signals, theories adapt. No result is not no progress. It is map-making by elimination. The unknown becomes smaller, even before it becomes named. Imagine searching for a hidden object in a large house. Each room checked carefully and ruled out is genuine advancement, even if the object remains unfound. Science often works exactly this way, room by room, energy by energy, parameter by parameter. Now let us return briefly to the image of those underground chambers waiting in stillness. Somewhere right now, detectors sit in darkness, watching for a flash smaller than intuition, rarer than habit, and more important than it would appear. Telescopes scan the sky, computers compare models, physicists argue politely and sometimes less politely over plots. All of it forms part of a global listening effort. Sooner or later, one of three broad outcomes may emerge. We detect dark matter directly. We discover a new theory explaining the evidence differently, or the answer proves stranger than either camp expects. History suggests never underestimating the third option. Some questions are scientific, some are personal, and some sit delightfully in between. What does dark matter feel like? After all, we have spoken about halos, cosmic webs, underground detectors, particle candidates, invisible mass, and streams of particles perhaps moving through your room at this very moment. It is only natural for the mind to bring all of that back to the body and ask a simple human question. If it is here, what is the sensation of it? The most likely answer, according to current evidence, is almost charmingly uneventful. Probably nothing at all. No pressure, no temperature shift, no tingling in the fingertips, no mysterious breeze through closed windows, no subtle cosmic handshake while you're trying to sleep. Dark matter, if it exists in the forms many scientists currently consider most plausible, appears to interact so weakly with ordinary matter that the human nervous system would register nothing. That can sound disappointing for perhaps half a second. Then it becomes fascinating, because it means something may be profoundly present without being experientially obvious, and that is not unusual in physics. Consider gravity. You do not feel gravity directly as a sensation organ might feel touch. What you feel is support forces, the chair pushing upward, the floor resisting your feet, the bed holding your weight. In free fall, gravity can feel strangely absent even while entirely in control. Consider air pressure. At sea level, thousands of kilograms of atmosphere press on your body over its total surface area, yet you're adapted to it and do not spend the day announcing, "Goodness, the air is still here." Consider the Earth's motion. Our planet rotates, orbits the Sun, moves with the Milky Way, and participates in larger cosmic motion. Yet you can rest quietly in a chair with no sense of racing through space. Many real things do not become sensations. Dark matter likely belongs to that category. Now let us examine why. Human senses evolved to detect features useful for survival at human scale. Touch, temperature, balance, sound, light, smell, taste, pain, motion, pressure changes, social signals, and the unmistakable sound of something breaking in another room. We are exquisitely tuned to practical life. We are not tuned to hypothetical weakly interacting galactic particles. If a dark matter particle passes through your hand without depositing meaningful energy, bending tissue, triggering receptors, changing chemistry, or causing force large enough for nerves to notice, then from the body's perspective, nothing happened. No signal, no report, no feeling. That does not mean no event occurred in a physical sense. It means the event did not rise to biological relevance. This distinction matters. Your body ignores vast numbers of molecular collisions every second. Air molecules strike your skin constantly. Photons hit surfaces. Background radiation passes by. Tiny vibrations occur in muscles and tissues. Cells exchange signals continuously. Consciousness receives only a filtered summary. If it did not, daily life would be unbearable. Imagine noticing every dust particle, every heartbeat fluctuation, every tiny thermal shift, every fabric fiber moving against skin. The brain wisely edits. Dark matter, if silent enough, would never make the final cut. There is another reason probably nothing is such a strong answer. Even our most advanced detectors struggle to sense possible dark matter interactions. These machines use purified materials, shielding, cryogenic temperatures, photomultipliers, precision electronics, and years of statistical analysis. If all that is required to notice a tiny candidate signal, then human skin and casual intuition are unlikely to outperform the laboratory. Your fingertips are talented. They are not a particle observatory. Now, some people hear this and wonder whether dark matter could create subtle, unexplained sensations that we misattribute to something else. Current evidence gives no reason to think so. Most mysterious bodily sensations have ordinary explanations: circulation changes, posture, fatigue, stress hormones, nerves compressing briefly, temperature shifts, dehydration, attention effects, anxiety, caffeine, muscle tension, or the timeless classic of having sat strangely for too long. Reality supplies many mundane causes before exotic ones. Science progresses partly by respecting that order. First test ordinary explanations, only then consider revolutionary hidden matter brushing your elbow. Another useful comparison is neutrinos. These real particles stream through you constantly, many originating from the sun. They're abundant, real, measurable, and mostly unnoticed. No one wakes and says, "I can feel today's neutrino levels." Dark matter may be similar in spirit, physically present, experientially absent. There is something calming about this. The universe can contain hidden complexity without demanding constant emotional response. Mystery need not intrude. Your room remains your room. The blanket remains warm. The pillow remains either acceptable or in need of one more adjustment. The body continues its familiar rhythms regardless of galactic halos. Now, let us entertain imagination carefully for a moment. Suppose humans had evolved specialized receptors for dark matter. What might experience be like? Perhaps certain directions would feel denser as Earth moved through the galactic halo. Perhaps annual modulation would become seasonal sensation. Perhaps city maps would include strong local flux, bring a hat. Fortunately or unfortunately, none of this appears to be the case. Evolution had other priorities. It selected for fruit recognition, edge detection, threat response, coordination, and social awareness. It did not allocate budget to halo particle awareness, reasonable management in hindsight. Still, the fact that we cannot feel dark matter says something profound about the limits of intuition. We often trust experience as the full measure of reality. If I cannot sense it, perhaps it is negligible. Yet much of the universe lies outside direct feeling. Infrared light, ultraviolet light, radio waves, X-rays, magnetic fields, quantum effects, the slow drift of continents, the expansion of space, and perhaps dark matter itself. Human experience is rich, but not exhaustive. Science extends sensation into territories biology never needed. There is also a philosophical comfort hidden here. Many people fear the unknown because they imagine it must be dramatic. But dark matter, if present all around us, appears astonishingly polite. It does not shout, it does not push furniture, it does not alter dreams, it does not interrupt tea. It may be one of the quietest major components of the cosmos. That is almost funny. The name sounds ominous. The behaviour sounds courteous. Now, to be precise, probably nothing remains tied to current leading models. If future discoveries reveal dark matter with unexpected interactions, the answer could become more nuanced. Science reserves the right to update itself. Perhaps some dark sector physics could have subtle detectable effects under rare conditions. Perhaps new experiments will uncover surprises. Perhaps our present assumptions will be refined. But based on what we know now, the everyday human sensory experience of dark matter is likely zero. No touch, no taste, no scent, no audible hum, no midnight tap on the shoulder, just absence of sensation amid possible presence of substance. That paradox is worth appreciating. Something can matter enormously on cosmic scales while meaning nothing to the senses. A mountain influences weather patterns, but may be invisible from behind a wall. A microbe can transform health while being unseen. A star guides seasons while feeling like a point of light. Dark matter may shape galaxies while feeling like absolutely nothing. Scale changes meaning. There is a subtle elegance in that sentence. What feels like nothing can still organize worlds, and perhaps that offers perspective for ordinary life as well. Small unseen habits shape futures. Quiet kindness alters days. Foundations are hidden beneath houses. Roots sustain forests from below. The invisible is not always empty. Strangely enough, one of the most mature things science has ever said may be this: we do not fully know what most of the universe is. That sentence can sound unsettling if heard the wrong way. It may seem like failure, uncertainty, or some grand confession that everything is broken and no one has been reading the instructions. I would suggest the opposite. It is a sign of intellectual adulthood. To say clearly and honestly, here is what we know, here is what we infer, here is what remains mysterious, is one of the highest forms of understanding available to any species, and so we come to a deeply human theme hiding inside the dark matter story. We live in a universe we barely understand, yet somehow, beautifully, we live in it anyway. Every morning people wake, make coffee, misplace keys, answer messages, water plants, worry about deadlines, laugh at jokes, fall in love, repair bicycles, study mathematics, and choose what to eat for dinner inside a cosmos whose dominant components are still partly unnamed. That contrast is worth lingering on. Daily life feels local and manageable. Reality is vast and unfinished. Both are true at once. For most of history, humanity assumed the world was much smaller and simpler than it is. The ground seemed flat enough locally. The sky looked like a dome. Stars appeared as lights pinned overhead. Earth felt central because we stood on it. Reasonable first impressions. Then knowledge widened the room. We learned Earth is round, then that it orbits the Sun, then that the Sun is one star among many in the Milky Way, then that the Milky Way is one galaxy among billions, then that visible matter may be only a minority share of the cosmic total. Again and again, understanding did not shrink us. It expanded context. That distinction matters. People often fear being small in the universe, as though scale determines meaning. But scale determines size, not significance. A page in a library can still hold a life-changing sentence. A seed can transform a landscape. A single neuron participates in thought. Likewise, humans can be physically tiny and intellectually extraordinary. We are small enough to fit in rooms and curious enough to infer cosmic webs. That combination is rare enough to celebrate. Dark matter sharpens this perspective because it reminds us that even our most successful scientific era has edges. We have mapped genomes, split atoms, landed probes on worlds, imaged black hole shadows, measured ancient radiation from the early universe, and built detectors deep underground searching for invisible particles. And still, much remains open. There is humility in that. But humility is not humiliation. Those two are often confused. Humiliation says, you know nothing. Humility says, you know much and there is more. One is discouraging, the other is energizing. Science, at its best, practices the second. Now let us consider what it means emotionally to live amid unresolved mystery. Some people crave complete certainty before they can feel calm, yet complete certainty has never been the human condition. Long before cosmology, people lived without full understanding of weather, disease, heredity, tectonics, electricity, or the causes of dreams. Life continued. Bread was baked, songs were sung, children were raised, friendships formed, mystery and meaning coexisted. They still do. You do not need a final theory of dark matter to enjoy rain on a window or to sleep peacefully tonight. You do not need to solve cosmic composition before appreciating kindness, tea, mathematics, trees, or music. The unknown can remain unknown without stealing the value of the known. That is a liberating truth. There is also something noble about participating in an unfinished story. Imagine being born after every scientific mystery had been solved, every mechanism catalogued, every frontier closed. Efficient, perhaps, also rather dull. Instead, we inhabit a time when major questions remain alive. What is dark matter? What is dark energy? How did consciousness arise? Are we alone? How does quantum gravity work? What new physics waits beyond current models? To live before answers arrive is not unfortunate. It is historically privileged. We get to wonder. Now, wonder should not be confused with confusion. We know a tremendous amount already. Dark matter is mysterious in identity, but the evidence for unseen gravitational effects is substantial. Likewise, many scientific fields possess extraordinary predictive power even where deeper philosophical questions remain. Airplanes fly without pilots solving metaphysics. Antibiotics work without complete theories of meaning. GPS functions because relativity is real enough to matter operationally. Knowledge need not be total to be transformative. That principle helps with life generally. You need not understand everything to move wisely within it. No one fully understands relationships, yet love happens. No one fully understands the economy, yet groceries are bought. No one fully understands the brain, yet thoughts continue arriving, often with surprising confidence. Partial understanding is normal civilization. Cosmology simply scales the lesson upward. Another gift of dark matter is that it exposes the limits of human intuition. We evolved to navigate forests, plains, weather, tools, faces, alliances, and immediate dangers. We did not evolve to reason naturally about invisible halos around galaxies or non-luminous matter, dominating cosmic structure. So when such ideas feel strange, that is not failure of intelligence, it is mismatch of training environment. Our ancestors needed to notice snakes, not weak-lensing statistics. This should make us kinder to ourselves when complex science feels unintuitive. Reality was not designed around instinct. That is why mathematics matters so much. Equations allow thought to travel where senses cannot. Telescopes allow eyes to extend beyond biology. Detectors allow touch to reach into particle realms. Statistics allow patterns to emerge from noise. Human beings became a species that manufactures extra senses. There is something magnificent in that phrase. We are toolmakers not only of objects but of perception. And with those tools we discovered that our visible world may rest inside deeper unseen structures. Now let us return briefly to the personal scale. Perhaps you are listening late at night, in a dim room, with tomorrow somewhere off in the distance. Around you are familiar things: walls, fabric, wood, glass, air, warmth. Maybe the low sound of distant traffic or wind. Everything seems ordinary. Yet ordinary life unfolds inside extraordinary context. Your body is built from star-forged atoms. Your planet orbits a star. That star circles a galaxy. The galaxy likely sits in a dark matter halo. The halo belongs to a larger cosmic web. The web expands through space-time shaped by ancient history. And still, your immediate task may simply be finding a comfortable sleeping position. This contrast is not absurd, it is beautiful. Meaning often lives in scales stacked together. The immense and the intimate, the cosmic and the domestic, the unresolved and the routine. Some worry that scientific mystery makes the universe cold. I think the opposite. A fully exhausted cosmos stripped of unknowns would feel colder to me than one still capable of surprise. Mystery keeps reality alive. Not mystery as superstition or fear. Mystery as frontier. Mystery as invitation. Mystery as the honest horizon of current understanding. There is also comfort in remembering that previous mysteries became knowledge. Lightning, disease transmission, stellar power, planetary motion, heredity, continental drift, radioactivity, exoplanets, gravitational waves, once uncertain, now understood far better. Dark matter may join that list someday. Children not yet born may learn in school what we still debate. They may regard our uncertainty with affectionate disbelief, the way we look back at earlier eras wondering how obvious truths once hid in plain sight. That possibility should feel exciting. We are not trapped in ignorance, we are located within progress. Now, progress is not guaranteed to be fast. The universe does not owe deadlines. Some answers take decades, some centuries, some perhaps longer. Still, inquiry accumulates. Each null result narrows options. Each map improves. Each detector listens better. Each theory sharpens. Each generation hands tools forward. That is how species think across time. And perhaps the deepest comfort of all is this. Even if we barely understand the the universe has still produced beings capable of trying. From hydrogen and gravity came stars. From stars came elements. From elements came chemistry. From chemistry came life. From life came minds. From minds came questions about dark matter. The cosmos may be obscure to itself, yet through us it has begun to notice. Even after decades of observation, theory, simulations, underground detectors, space telescopes, precision measurements, and enough careful debate to power several academic careers indefinitely, one central fact remains. We still do not know what dark matter is. We know why scientists take it seriously. We know where its gravitational fingerprints appear. We know it helps explain a remarkable range of cosmic behaviour. We know the standard cosmological model works impressively well with it included. And yet the identity of dark matter itself remains unresolved. That combination can feel unusual to people outside science. How can something be strongly supported and still unknown? But this happens more often than it seems. You may know there is an animal in the attic from noises, scratches, displaced insulation, and mysterious midnight thumps long before knowing whether it is a squirrel, raccoon, or an exceptionally motivated pigeon. Evidence for presence and knowledge of identity are different stages. Dark matter appears to be in exactly that situation. So let us spend some calm time with the honest frontier. What we still do not know, first, and most obviously, what particle, substance, or phenomenon is dark matter? This is the headline mystery. Is it a new fundamental particle beyond the current standard model of particle physics? Is it a family of particles? Is it something ultralight like an axion? Something heavier like classic WIMP candidates? Something hidden in a dark sector with its own forces? Something involving primordial black holes in limited amounts? Something stranger not yet elegantly named? At present, no option has won conclusively. That matters because once identity is known, many other questions become easier. Second, how massive is each dark matter particle if particles are the correct picture? This question changes everything from detector design to expected abundance. A lighter particle means more particles are needed to make the same total mass. A heavier particle means fewer are needed. Same cosmic weight, different cosmic census. Imagine asking whether a warehouse contains feathers or anvils. Total mass alone does not reveal count. Likewise, local dark matter density does not tell us particle number until mass is known. Third, how does dark matter interact, if at all, beyond gravity? Gravity is the evidence we see clearly. But does dark matter also interact weakly with ordinary matter through other forces? Does it self-interact with other dark matter particles? Can it decay? Can it annihilate? Can it convert under special conditions? These questions are crucial. If interactions exist, even faint ones, experiments may detect them. If interactions are almost non-existent, detection becomes harder and theory shifts. Fourth, is dark matter one thing or many things? Human language often pressures us towards singular nouns. We say water, sand, wood, weather, traffic, and dark matter, as though categories must be tidy. Nature is not obligated to comply. Ordinary matter includes electrons, quarks, neutrinos, atoms, molecules, plasma, solids, gases, and astonishingly complicated arrangements such as houseplants and tax paperwork. Why should the dark sector, if it exists, be simpler? There may be multiple components with different behaviours. Some could be cold and slow-moving, some warm and faster-moving, some interacting slightly, some nearly invisible even to other dark matter. At present, we do not know. Fifth, how exactly is dark matter distributed on small scales? On large scales, the halo and web picture works well, but smaller galactic scales still involve active research. How many small sub-halos should exist around galaxies like the Milky Way? Why do some dwarf galaxies look the way they do? How do ordinary astrophysical processes such as supernova feedback alter what we infer? These are not trivial bookkeeping details. They help test whether our model is complete. Sometimes great theories succeed broadly, but need refinement locally. Sometimes local tensions hint at deeper revision. Science pays attention to both possibilities. Sixth, could some of the evidence instead reflect modified gravity? This remains an active question. Dark matter is the leading mainstream explanation, but alternative frameworks continue exploring whether gravity changes under certain conditions or scales. Many such models face challenges matching all available data simultaneously, yet their existence is healthy for science. Competing explanations sharpen standards. If dark matter remains strongest after fair challenge, confidence grows. If alternatives reveal weaknesses, progress still occurs. Either way, evidence wins. Seventh, how was dark matter produced in the early universe? Suppose it is a particle. Then how did it arise? Was it thermally produced in the hot young cosmos, generated through field dynamics, created during phase transitions, left over from inflation-era physics, produced asymmetrically the way ordinary matter has matter-antimatter puzzles of its own? This question links cosmology with particle physics. Dark matter may be not only something present now, but a fossil clue from the earliest moments of cosmic history. That is one reason researchers care so deeply. To solve dark matter may also reveal ancient chapters of the universe. Eighth, why does ordinary matter exist in the proportion it does relative to dark matter? The visible world is rich with chemistry, stars, biology, oceans, forests, and listeners in bed wondering about cosmology. Yet ordinary matter appears to be a minority component of total cosmic matter. Why this ratio, coincidence, shared origin, selection effect, deep principle, unknown. Sometimes the most familiar ingredient becomes the strangest question. Ninth, can dark matter be detected directly at all? This sounds obvious, but it is profound. Maybe current detectors are simply not sensitive enough. Maybe we're searching in the wrong mass range. Maybe interactions are rarer than expected. Maybe detection requires new technology not yet invented. Maybe the concept itself needs reframing. History offers many examples where tools had to catch up to theory. Microbes awaited microscopes. Radio waves awaited suitable apparatus. Exoplanets awaited precision methods. Dark matter may be waiting for its instrument. 10th, how will we know when we have truly found it? This is not as simple as it sounds. Science demands robust confirmation. A single anomaly is not enough. A curious bump in data is not enough. A headline is certainly not enough. A convincing discovery would likely require repeatability, independent verification, consistency across methods, and strong exclusion of mundane explanations. In other words, the answer must survive skepticism. That is how fragile excitement becomes durable knowledge. Now, let us pause and appreciate something important. These unknowns do not mean we know nothing. They mean we know the shape of the mystery. That is progress. A child asking what is in the box knows less than a scientist saying, the box has this weight, rattles at this frequency, responds to magnets in this way, and likely contains one of three classes of object. Constraints are knowledge. Ruling things out is knowledge. Narrowing options is knowledge. Precision ignorance is far better than vague certainty. Dark matter research today often lives in that realm. Precision ignorance. There is dignity in it. Outside science, people sometimes treat uncertainty as embarrassment. In research, uncertainty properly measured is an achievement. It tells future work where to aim. Imagine sailing with no map. Then imagine sailing with a map showing coastlines clearly, but one inland region labelled unexplored. The second situation is vastly better, even though mystery remains. That is where we are. The coastlines of evidence are strong. The interior still awaits survey. There is also emotional comfort in admitting limits. Many anxieties come from feeling we must know everything immediately. The universe itself does not operate that way. Understanding often arrives in layers. First clue, then pattern, then model, then test, then refinement, then surprise, then better model. Dark matter may simply be in the middle of that sequence. Perhaps future students will read about our era as the age when humanity knew dark matter's gravitational role, but had not yet identified its substance. Perhaps they will smile at our candidate lists the way we smile at older diagrams of atoms, or perhaps they will discover the truth is stranger than all current options. The universe has a habit of exceeding tidy guesses. Now bring this gently back to the present moment. You're listening in a room built from ordinary matter, on a planet orbiting one star, inside a galaxy likely wrapped in unseen mass, while one of the major components of reality remains unnamed. And yet the room is still calm, the floor still holds, breath still rises and falls, mystery does not prevent peace. After all these unknowns, evidence, questions, and cosmic scales, what should it mean personally that you may be surrounded by something invisible right now? Tonight, we began with a simple question. Are you surrounded by dark matter right now? At first, it sounded like the kind of idea meant to startle. Invisible matter in the room, particles passing through walls, ancient cosmic substance moving through your body unnoticed. The phrase carries a certain dramatic flair, the sort of wording that makes human imagination immediately check the corners of the ceiling. And yet, after travelling through galaxies, halos, clusters, cosmic webs, underground laboratories, equations, uncertainties, and all the careful evidence that brought scientists here, the answer feels gentler than it first appeared. Most likely, yes. And most likely it changes nothing about the comfort of this moment. That may be the most beautiful part of the story. The universe can contain immense hidden realities without disturbing the quietness of an ordinary night. Around you now there may be air you cannot see, radio signals you cannot feel, gravity you cannot touch, neutrinos passing silently through the earth, and perhaps dark matter moving with equal politeness through your small corner of the cosmos. Yet the blanket is still warm, the room is still still, your breathing still rises and falls in its familiar rhythm. Mystery and peace are able to coexist. We often imagine the unknown as something loud, dramatic, threatening, or urgent, but many of the deepest truths in nature are quiet. Gravity never shouts, time never knocks. The Earth rotates without asking for applause. Galaxies turn in silence. Dark matter, if it truly fills halos and helps shape the universe, may be one of the quietest great actors of them all. There is something comforting in that. Not everything important demands attention. Some things hold worlds together invisibly. Some forces work patiently in the background. Some truths become real long before they become obvious. And perhaps that idea reaches beyond astronomy. Much of what sustains life is subtle. Trust often grows quietly. Healing can be gradual. Habits shape futures without fanfare. Roots support forests underground where no one applauds them. Foundations hold houses from below where no guest stops to admire the concrete. The hidden is not always empty. Sometimes the hidden is what makes everything else possible. We also discovered something else tonight. Living in a universe we do not fully understand is not a tragedy. It is normal. It has always been normal. Our ancestors lived beneath stars they could not explain. We live inside galaxies we only partly understand. Future generations will inherit mysteries we cannot yet name. Ignorance honestly faced is not failure, it is frontier, and frontier can be beautiful. There may come a day when dark matter is identified clearly, a particle detected, a theory confirmed, a better framework established, textbooks rewritten, lectures updated, arguments settled for at least 15 minutes before new ones begin. Children in classrooms may one day learn the answer casually, unaware that earlier generations once stood in suspense, That day may come. Until then, we live in the interesting part. We live in the era where clues are strong, the identity remains open, detectors are listening, telescopes are watching, and the universe still has secrets large enough to humble confidence. That is a gift, if you let it be. Because certainty can close doors, wonder keeps them open. Now, think for a moment about where you are. Perhaps in Wrocław, perhaps somewhere far from there. Maybe under a roof in a sleeping neighbourhood. Maybe high above streets in an apartment tower. Maybe in countryside quiet where only wind moves outside. Maybe travelling with unfamiliar walls and a borrowed pillow. Whatever place holds you tonight, it is also located in a far larger address. On Earth, in the solar system, inside the Milky Way, within a likely dark matter halo, inside a cosmic web stretching across distances too large for intuition. All while you rest in one room, the intimate and the immense are happening together. That is worth remembering when life feels narrow. Your immediate concerns are real, but they are not the whole frame. There is more room around them than it sometimes seems, and if dark matter is passing through this room now, as many models suggest, it does so without demand. It asks nothing of you. It does not require belief to continue existing. It does not need your worry. It does not interrupt sleep. It simply drifts. Perhaps there is wisdom in that too. Not every presence needs reaction. Not every unknown needs fear. Not every unanswered question must be solved before rest is allowed. Some mysteries can remain mysteries tonight. You can let them keep watch while you sleep. Science, at its best, does not only provide facts, it also offers perspective. It reminds us that we are local beings inside vast systems, temporary minds inside ancient processes, curious creatures able to notice patterns far larger than ourselves. From atoms made in stars, life emerged. From life emerged thought. From thought emerged the question, what invisible matter surrounds us now? And somewhere in that chain the universe became able to wonder about itself. That is no small thing. So as the night deepens, you do not need to picture threatening darkness around you. Picture instead a calm and layered reality. Familiar objects near at hand, hidden physics passing softly through them, a galaxy turning overhead, ancient structures holding shape across space, unknowns waiting patiently for future minds, and here, in the middle of all that, one person resting. That is enough. Thank you for spending this time with me on Science for Sleep. If this journey brought you calm, curiosity, or good company in the late hours, I'd be grateful if you liked the video, subscribed, and returned again when you need another gentle trip through reality. For now, allow the questions to loosen. Let the room be simple again. Let the universe continue its work without supervision. And while invisible things drift quietly through the dark, you can drift too.